Okay. Well, I'm sorry. That's Sam. I have me as well. Right. No, yeah.
I didn't get to do the line. It's really, I'm good with that, right? Because it's like, you in the free now. So it easily should be really popular. So easily there's not the
Yeah, but some of the time.
I see that. I don't think it's quite. Yes, so I know what you mean.
When you run it, they don't.
It's actually doing what they call or it should be. Yeah, we will let them know where it is. I think it's crazy. I need to know. So it's the contrast that we're done saying about it. I just was thinking I think it should, we don't have part of this 9.
Okay.
Receiver.
Okay.
So we're going to do search and consider and look at any
Yes.
I need to question.
Yeah. How we
Boost. I think we should. I mean, governments didn't have any different. They should have these. The same, smoking the same things. At the same time. No, they were doing. There should be an issue. They don't want to be there. This is also that would be by and. You're. I think, yeah, it's, I think it's the building. So this is very very. So you just grab this that's just gonna go back. I think it's going to says the distance.
Well, it sounds like that for, or,
Then are.
creating more art in the state. But it's been to this forward right now, but they always, we're gonna do one more.
Exactly.
Okay, sure. Otherwise, I don't know.
I will also get it from those markets. One message here, you talk.
Yeah.
But was very good to do the first time about the staff. There's all actually this thing. There's no matter the style.
Possible. Yeah.
It's not. How are you much of one?
Yeah, you mean,
They're just like my messages that are actually. You can pull over all. And I, alright, basically, yeah, you're so I just.
yeah.
Alright. Yeah. So.
Yeah.
I wonder if you're further out. Phase and the frequency at some of them are operators that you see here. This is
All of that.
That's what I'm saying, we could probably eventually. Maybe like that. This is all, yeah. Like the problem right now, here's a.
Yeah, I understand.
Yeah. Part of the affairs.
but there's individual functions.
No, it's,
You know, that comes. The function does
it's just fine because,
you know,
you're all of it, it's allowed to do so.
yeah, but I'm saying.
Yeah, I think it's pretty exciting, it's really, so then each.
There's no reason to be done.
So the.
30 days, right?
Yeah.
I would keep yes,
Well, it's not as more than a relationship. I think the right government is not to use the fingers. I just wanted to make sure that.
Yeah, so it wasn't like
you guys had.
an error. No, we're working.
No.
It's the future.
I think
I've been told.
So I think we're asked to do this. Just remember that, that's girls. So, yeah, that's the girls.
yes,
I was hoping.
yeah.
So.
Anyone is left.
Yeah, but I mean,
You want to have.
that is, I want to run this.
That was my trial to see.
I guess that's such.
See. Yeah, negative. Yeah, it's pretty negative.
I swear, I had tried.
How's it going?
Yeah, I have.
I'll wait until I guess. You know, I'm just gonna try it again.
I'll be great. The video.
No, it easily is.
Jesus.
5 minutes for a second.
Let's just see what
I may legitimately be.
Probably one, but they're not one, so. Please.
Yeah, that's.
Yeah.
Shouldn't have been.
But it's not. The next conversation I have. So that's.
You all can get down to the.
I say it for. If it wants to really hard.
Yeah. Well, you sure, perfect call today.
I'm sorry, I'm sorry, you have that. Record. See, you're trying to get a little better when we get. Okay. I guess Tuesday, what do you think? Where are we then? We're just being bold and one. What do you think we're that?
And the post office, it's very great.
There, that.
There's, on Broadway, there's, Broad complex. So it's also the, I can stand by with her, just. And then there's that we made a lot of. Oh, yeah, and I mean, it's, there's a carry thing there, where there's no reason that had like some of the I'm trying to style the standards. It's in. It's the one, yes, okay, I mean, like, we really how far us has. Zero. It's like making this time, check out if this is together.
I'm just.
That's how it's. This is like describing.
There is a shot that is the shape of it. So, does that look like G?
Oh my God. We should go check. Outside, there.
You see it now? You see it? Yeah. It's sound.
It's like.
No, it's sometimes, but I have my. Never been sold. I saw this, I said it's freaking.
Which is.
But this is trying to buy. They do not go. That's. This is one of the next time
Well, maybe I'll do that way.
Yeah.
I'll get some. I'm trying to make it all.
This year. Oh, next time. I'm just because of our great piece of that. So that yeah, that's just sort of down, yeah, of course.
I still like everything. The main crooks.
I don't think but it has.
Well, I do like that. There's not other. I don't see else there. We also saw all the right there.
I didn't hear, I was like, one hand, right?
Yeah, that's it.
As I've always said, where's my favorite? Like,
Okay, I was thinking four. I couldn't because I was only thinking of the, and I was like.
Yeah, it's like.
I thought you were about to say, I just figured. I watched that. It was fun.
I'd say medium hot is manageable. When you get above hot. It's just. So people are very, they talk about you, it's very,
Congratulations, it's one of the rock when you go up.
yeah, it's time to. Okay, I'll talk.
Oh, yes. So we did all of that.
But I do. You have a picture, how you.
I heard that, how do you say, how you cry?
On my visit here, I had the Broadway, we're very busy, a lot of people. And I was like sweating, in my chair.
Well, was it happy?
It was so hot, it was bad, it wasn't good, it was just hot, wasn't bad. It was perfect hot.
Was it last time?
If you want to rest on shape, rest on shape. You got, it's like you know spot. You know, I mean, it's attached to a diet, which is one, you hold the bar in that, and two, people go to that bar in America.
So a lot of people travel, try to get out.
It's, to me, it's a little bit of a longer that.
Oh, damn.
That's not for a beer.
They got their own kind of part.
It is that.
I mean, if you run those,
It really rushes. That's the one thing. So,
We're gonna put that here. I mean, I feel like they're really like, you know, actually not fear to like bring up, I mean, you're like, everywhere, you know, you should look right.
Yeah.
I feel like.
I should have understood you.
I guess, more uncertain times. And
Yeah.
You're playing on. Oh, yes. I thought that's 2 weeks to be like perfect time to, after the actually, I did it, the fact. Once. I have. I do have. It's one of those, like, there's like, I won't remember. But I will.
That's like, there's some funny on it, and that's like. That would be one done, they're really the same folder, shot it, yeah. You got kind of.
I'm sorry, I hadn't heard that.
Okay, are you feeling like you would kind of look at that? I don't know, sorry. I wasn't one, it's supposed to be, and her writing her, so this.
Oh, Jackson.
It is one. I'm doing something, I'm so it's like. Basically, questions now, like. I wish I would have right now, instead of this, it's like, But rather than like things that comes from this. Yeah. I didn't know these from. I don't. Like 2 weeks ago. Well. We have the. Yeah, I don't say where. But yeah.
You.
So.
Yes. Thank you, good question.
Yes. Actually,
So.
So long
So really, just so that. You just like a new person.
And right now it's, I want. Like, this is like value that should be, this bar, I'm trying to have. Is volume is zero.
Well, I'm not sample, but I do that.
Mine's,
You said that.
so if it's higher, there's less, okay, this is like zone 18, that's the standard.
They're
The scale has even.
they were one of the first of women's back.
Minus the beach.
That was like 50 seconds. Back in the. It's not a real thing they had. They set up a special now, we're always in the experience. Like I went to the third grade and they would get the audience for blue time. What it was like, I said, right to. Right, you just put it over. Yeah. It's not something they start. I was like, I told you, stay there. Yeah, it's still. It's like I did all that.
So you're making it. Improve and that's how. Say that you can, but you don't finish that 30. You did it. And you did it. I mean, you graduated 2 times.
Just a little bit down, but not all the way down, I do like this side.
That's the.
Thank you. Yeah.
Steve,
you seeing it?
Yeah, could you grab it from further up? It's not the one that Dave Wright shared, it's the true summer school one.
The original one?
It's the original.
Yeah.
That is good. But, yeah, it's a visual. And then, it's busy. Like, no, like, all.
Hi, Bjorn.
Hello. Can you hear me? Oh, okay. I can't hear you all of a sudden.
Okay, can you hear me now?
Yes, now I can hear you.
The meeting owl is a little bit temperamental, it seems, with direction. Yeah, would you be ready to go? Anytime?
Yeah, absolutely.
Well then, let's get started for the morning. It's my pleasure to introduce Bjorn Larsen, who's a graduate student at Yale University. Bjorn, amongst many other things, has worked on continuous wave searches for pulsar time arrays, has worked on stochastic background searches, and this morning his true heart, I think, is with noise. He knows all about chromatic noise sources, how to mitigate them, how to include them in gravitational wave searches to improve our parameter estimation. So it's my pleasure to introduce Bjorn, who's going to tell us all about noise, and let's give him a round of applause.
Hey, thanks so much, Steve. Yeah, I'm happy to be here today to talk about this. I'll go ahead and share. Okay. I can see this is visible. So yeah, we're going to talk today about various noise sources in PTAs and how to model and mitigate them. I know you've all heard a lot about just the various different types of gravitational wave signals and searches and how to constrain them, how to get these astrophysical inferences out of them. We'll hear more about continuous waves later today too. But noise is really underlying everything. And I love this visual from the NSF during the 2023 announcement, just in terms of like showing our beautiful detector here and all the links between the different pulsars representing the cross correlations and just showing how the whole PTA is embedded within our galaxy. The galaxy itself is, just so beautiful with the whole, all of the various different stars and the gas in between all the pulsars too. And there's a lot that we can learn from pulsar timing about just this whole medium of the galaxy itself. But when it comes to actually trying to measure gravitational wave background, all of the galaxy in between the pulsars is a big dumpster fire. And we sometimes sweep it under the rug when we talk about gravitational wave analyses in general, but today we're going to completely remove that rug and look at everything that's underneath and try to clean it up. And along that line, I also stole this image from Abhimanyu Susubanan at the IPTA meeting, which is again showing the same story of we love to talk about our gravitational wave analyses, look at the Hellings and Downs curve, which is itself a very robust statistical test against various noise sources. But in order to be able to resolve this in general, we have to deal with all of these various different effects of the pulsar, the interstellar medium, the whole process of generating the TOAs and mitigating the noise there. And it's nice to sweep it under the rug, but we're going to talk about it a little bit more today. I should also talk about actually what do we mean by noise, because there's a lot of different ways that we might just use the word noise in PTAs that just goes alongside all of the jargon we already have. And there's kind of two different contexts in which we talk about noise. One is, of course, just in terms of, some type of signal being usually a stochastic process and something that is not really like a resolvable signal, like a continuous wave. Instead, it would be something that we can't really resolve, but is present in our data analysis. So, for example, we talk about white noise versus red noise, white noise having just a flat spectrum um, across frequency, equal power at high and low frequencies, versus we might have something like red noise, which will have more power at low frequencies. And so those are kind of distinguished here in this plot. And the upper panels, just in terms of the spectral content across frequency, and then the lower panels show examples of what that might look like in the time domain. White noise is basically just randomly fluctuating around, but doesn't move over time in terms of the mean of the signal, whereas, of course, our red noise is this much lower frequency process. And so in this sense, the gravitational wave background is itself, we sometimes call it a red noise or a common red noise process that has cross correlations between the pulsars. But the main context in which I think we usually talk about noise is just everything that we need to account for in our data analysis besides the signal itself that we're looking for. And in terms of our, you know, and in terms of our actual modeling, you know, this is most simply represented in this equation here. We have our timing residuals on the left, and then we fit that with some model on our right, which is just whatever our signal is. That could be our gravitational wave background, that could be continuous waves, it could be both, could be something else. And then everything else that we have to include in our model, N is our noise. And so for a more concrete example, you've probably seen an equation like this at some point earlier in the school, where we will treat our timing residuals with a timing model. We'll have some intrinsic red noise, some white noise, and our gravitational wave background. And so just everything else in here is our noise, except for the gravitational wave background signal we're looking for. That said, we can also have potentially some analysis where, say, you know, we've already found a gravitational wave background, and now we're interested in studying some aspect of pulsar physics, say the binary orbital model for a particular pulsar, because we want to do some tests of general relativity. And if we're going to model this in a same framework, we might have a case where the timing model itself is the signal we're trying to measure, and then everything else in here is our noise, including the gravitational wave background. So one person's signal is another person's noise. In the end, when we're doing noise modeling, we're kind of modeling the entire universe that is going to be affecting our timing residuals, except for the thing that we're trying to measure, and we want to measure that too. So it sort of leads to this philosophy of just modeling everything in the most harmonious way that we can. So in practice, what does a pulsar timing array noise budget look like? What are the things that we actually usually have to worry about for a gravitational wave search, for example? And there's a variety of effects that go all the way from the pulsar itself in the top left and the interactions it has in its own magnetosphere, its own spin physics, and interactions with its binary orbital companion, if it has one. There's the propagation effects in the interstellar medium, which take up the biggest part of the panel, I'd like to think, because it's in some way some of the messiest parts to try to deal with in our analyses. And so we have effects like dispersion and scattering, which are affecting our pulse profiles we see in the bottom as a function of radio frequency. This is the thing that about most of the interstellar propagation effects that helps us out, is that they tend to be radio frequency dependent. So just by getting more measurements at high and low radio frequencies, we can resolve these effects better and better distinguish them from other effects such as gravitational waves. And so that's what we usually call chromatic, is the radio frequency noise, and as opposed to achromatic noise. So the more radio frequency bandwidth we have, the better. And then there's all these various different terrestrial effects, making sure that we have accurate solar system models so we can translate to the inertial reference frame, not having any clock errors or whatever sort of any type of noise at the receiver itself, just in terms of the system temperature of your receiver. If you have noise there, that will get amplified and make it harder to measure your pulse profile. And all of these effects are, if they're large enough, could show up in your analyses, and we want to make sure we have models that are capable of dealing with those too. I have another illustration of these various different noise sources too, and some of the ways that we try to categorize them a little bit better. So in terms of what types of noise sources create like a white noise spectrum versus a red noise spectrum. So for example, in the white noise domain, we have these various receiver effects I was talking about. In terms of system temperature, for example, if you have a higher system temperature, you can't measure your pulse profile against with the template quite as well, and so you'll get some random errors there. There's also this phenomenon of pulse jitter that introduces white noise in our analysis, just from individual pulses having random shapes, which if you average all of them together over the course of a single observation of a pulsar for 30 minutes or 15 minutes or an hour, then the effect of those random pulse variations will be mitigated, but it's always there at some small level. So that's another white noise effect. As for red noise, we kind of, as I mentioned, can group those into chromatic versus achromatic noise. And so another more concrete definition, and kind of the biggest source of chromatic noise we worry about, is this effect specifically of interstellar dispersion, or the dispersion measure is this quantity defined in the top equation, where Ne is the free electron density in the interstellar medium. If you integrate that along the total line of sight from the Earth to the pulsar, that gives you the total dispersion measure, how much the pulse is going to be dispersed along that line of sight. And you can convert that into a time delay via the bottom equation. And the main thing is that this time delay we get from dispersion is proportional to the dispersion measure, alongside the inverse of the radio frequency squared. And that is a pretty well-defined relationship just from the plasma dispersion relation. So that is an effect that we know how to model pretty well, but the difficult part is measuring this dispersion measure over time. And that's one of the challenges for noise modeling. And alongside this, we also have a variety of other sources of chromatic effects. So alongside the interstellar medium, the interplanetary medium, or the solar wind, introduces itself dispersion effects, and the time delay due to the solar dispersion is going to be the same as the interstellar dispersion, but the time dependence from the interplanetary medium, just due to the Earth's orbit around the sun, is going to cause a very different time dependence that we have to deal with. And then even messier are different types of refraction or diffraction effects you might get just as these pulses travel through inhomogeneous interstellar medium. If you have any sort of gradient in the index of refraction along the line of sight, you can get these multipath propagation effects. And that is going to also impact the shape of your pulse profile in a way that is not as straightforward to model as this inverse frequency squared effect. And I'll touch more on this later, but the collective, the main collective impact on your TOA is from this is this scattering, this pulse scattering effect. And this is a bit nastier to try to model. And then you even get these, various types of pulsar magnetospheric events that happen in certain pulsars. And so these could be intrinsic to the pulsar, not even necessarily interstellar in origin, although they could be interstellar in origin too. But the point is we sometimes get just weird like events that we see in certain pulsars where their pulse profiles change in a way that is also chromatic. So we have to deal with this too. The achromatic noise, we also try to categorize into a way, split it up into intrinsic sources of noise. Everything so far I've talked about is an intrinsic versus intrinsic noise source versus these common noise sources where you could have noise that is impacting all the pulsars at once. And so for the intrinsic noise, you can have, for example, just the effects within the pulsar, the neutron star itself. One of the main types of noise that we talk about is spin noise. And this is really strong in canonical pulsars, where you can have these random interactions essentially between the superfluid core of the neutron star and the crust of the neutron star, where it will create these stochastic drifts in the spin of the pulsar over time. And so that will just manifest as some achromatic red noise. And that is also that's really dependent on or proportional to how fast the pulsar is radiating energy just in terms of its spin down. So this is a very weak effect in millisecond pulsars, but it is much stronger in canonical pulsars. We believe it's present at some level in millisecond pulsars too. And then additionally, there's these binary orbital effects that I talked about before. Just in terms of the, we have deterministic models for the pulsar binary orbit, but depending on, it can get very messy, especially if we have these so-called black widow pulsars, which are radiating so strongly to their companion that they're ablating material off of the companion that could change the mass or the distribution of mass around your pulsar over time and cause really nasty effects that we are still, as a community, working on how to model those correctly. So that's if we, depending on how good our deterministic models are, this could introduce a lot of achromatic red noise. Another hypothesized source of noise in millisecond pulsars could be if we have asteroid belt around the pulsars, and that will just introduce these just stochastic variations in just minute like gravitational effects around the pulsar, which will impact the spin. The main thing in the end that would distinguish this from an intrinsic spin noise of the neutron star would be if you can, is that an asteroid belt should be stationary if observed over a long enough period of time, whereas the intrinsic spin noise is non-stationary. And in the end, these are all various types of intrinsic noise we can get that are just purely achromatic because they're happening at the pulsar itself. And then finally, we have our common noise sources, which I alluded to, clock errors, if we have some mismatch in our terrestrial time standards, as well as solar system ephemeris errors, just any errors in translating to the solar system barycenter. And these are effects that could impact the full that would impact the whole PTA at once in the same way. But the key thing is that they will have a different cross correlation than our gravitational wave background. Instead of looking like a Hellings and Downs correlation for a clock error, it would be monopolar. It would just introduce the same exact signal in the time domain in every pulsar at once. Whereas for solar system ephemeris error, it would be a dipolar correlation. So these are ways that we've been able as a community to distinguish between these different effects in the past, just based on the cross correlations. And we search for these effects. We can't do so until we get time to the gravitational wave background analysis. And then we search for all these different effects at once and see if they're significant. And at the moment, with the current data sets, we do not have any significant clock or solar system ephemeris errors, so we don't need to, we don't have to account for them, but it's always good to search for them and see if they become significant. And then, of course, finally, we have our gravitational wave background, which is oftentimes going to be the signal that we search for. But if we are doing some more type of complicated search, such as a continuous wave search, then our gravitational wave background is also a source of noise. And accounting for the Hellings and Downs cross correlations between all the pulsars is, in many senses, a much better noise model than just treating it as a common uncorrelated noise, because we're better accounting for just this relative phase information between the different pulsars. And as much as this is an attempt to try to cleanly categorize all of these different noise sources, there's really, it's not really so cleanly categorized in the end, because a lot of these effects could be actually chromatic in some way, such as jitter is actually known to have some frequency dependence. So that needs to be accounted for in terms of a chromatic model potentially. Binary orbital noise might actually be chromatic in some sense if there is a lot of local interplanetary medium at the pulsar that is impacting our analyses. There's some achromatic component of these magnetospheric events, potentially. A lot of these noise sources that I talked about that I called red noise, actually may have a white spectrum in some sense, or look more like a white noise, especially if the effect is chromatic. They tend to have much shallower spectra in general than some of the more intrinsic achromatic pulsar noise sources, such as the neutron star spin noise. And then some of these effects also may have some common or quasi-common component. So, for example, in recent years, there's been a lot of talk about if the spin noise in millisecond pulsars has essentially a common sort of manifestation, because if all millisecond pulsars have around the same level of spin noise, then that could look like a common noise in the PTA. And so one way to try to address that is with hierarchical models that account for just the population distribution of noise in millisecond pulsars. And the solar wind also is affecting all of our pulsars in the array in slightly different ways, depending on how closely each pulsar passes to the sun. But in a sense, all pulsars still are seeing the same global solar wind, so that may have some common correlated component too. So in the end, it's kind of a mess to try to understand and account for each of these different types of noise individually. But we are going to try to do that anyway. And in the end, why do we even, why is this so important? Besides the fact that, we want to do the best job we can and mitigate all of these sources to measure gravitational waves, but we still have a problem in the current era PTA measurements where there's various different types of noise models that are accepted to use in the literature. And depending on which choice of noise model you use will impact your gravitational wave measurements. So this is an example from the 15-year dataset paper where we have, in this case, these are two different models for dispersion. And both models are good models in the sense they've been tested, they've been used in different contexts in the literature, but just the detailed differences between them leads to different measurements of the amplitude and spectral index of the gravitational wave background. And this is going to have potentially a major impact on your astrophysical interpretations or cosmological interpretations of that signal, based, for example, on how close your posteriors are to a supermassive black hole binary hypothesis. Our 13/3 value is indicated in the vertical line. So in this case, this DMGP model indicated in red gives a slightly more consistent value, consistent posterior, and the standard model that we've used in nanograv, DMX, gives you a slightly further away posterior. And so we want to have a good understanding behind these different models and understand what they're doing and which seems to be more reliable in the long run because of how critical this is for our interpretations. Okay, so that was kind of the background of everything in terms of noise. I can't see the room super well, but if anybody has any questions at any point, I think now might be a good point to stop, just in case there are any.
Any questions from you at this point?
Oh yeah, Martin has a question. Probably, yeah, best to come up.
Hey Bjorn, I've heard a lot about the differences between DMX and DMGP, and I know that I don't really know how DMX is calculated, but I know that DMGP is calculating the DM indices through a Gaussian process. Is that correct?
Yes.
Okay, and then how is DMX calculated?
So DMX is it's treated in the timing model. It's essentially fitting a set of a separate DM parameter for each observation epoch where there's multiple frequencies. So if you have one, you at the Green Bank telescope, for example, they do one observation at the lower frequency receiver at 800 megahertz, and then that's separated by a couple of days with an observation at the higher frequency receiver at 1400 megahertz. And then with the DMX model, we just take both of those observations and we fit a single DM parameter to both of those. And it's just and we do that for every single grouping of multi-frequency observations. So it's this piecewise constant model. And we just fit whatever is the best fit values in the timing model at the time of the timing analysis. But then during our noise and our gravitational wave background analyses, those are allowed to vary using this linear timing model that we have in Enterprise and Discovery. So and that's treated with this, how we do with the timing model where everything is given an infinitely large prior on all of these perturbations to the timing parameters. So the DMX model is able to really absorb any type of trend that looks like it's an inverse frequency squared at each grouping of observations. And I have a few more slides showing some comparisons between DMX and DMGP later as well.
Okay, thank you.
Okay. Um, yeah, if there's nobody else, I'm going to continue. But yeah, if anybody has questions at any point, they should feel free to interrupt. So moving on, I do want to talk a little bit about the different sort of paradigms of accounting for noise in PTAs because I'm mostly going to be talking about modeling, how to sort of account for these models during our gravitational wave analyses, but there's also other approaches to thinking about noise. So one of these approaches is taking that whole, taking all of those individual sources of noise I talked about and actually trying to really understand and model the physics behind them. And so, for example, and there's a lot of, this is actually one of the main goals of the noise budget working group in Nanograph. For example, trying to study the effects of the interstellar medium in terms of scintillation measurements and being able to develop methods to mitigate scattering in the pulse profile domain directly. And any breakthroughs that we can make in this territory, any breakthroughs are going to have huge benefits because then that can mean a whole type of source of noise that can get mitigated at an earlier stage of the analysis and will not reduce sensitivity in our later downstream analyses so much. And the various different sources of noise and strategies for mitigating them directly is covered really well in this recent fundamental noise processes for PTAs paper by Jim Cordes, led by Jim Cordes, which I definitely recommend others to check out if they're interested in this. This is the most far away from my own expertise, so I won't be talking about it so much for the rest of this talk, but it's worth knowing that people are working on direct mitigation strategies for some of these types of noise. We can also understand different types of noise in terms of theoretical sensitivity curves, like we would have in LIGO and LISA. And these are really nice for being able to forecast the sensitivity of a PTA given different types of noise sources and also understanding the effects of different types of noise. And so we can see, for example, just in this plot, the sensitivity curve, if we just have white noise, is going to dip much lower to much lower gravitational wave strains. But red and white noise together is going to, or adding red noise on top of this, I should say, is going to reduce our low frequency sensitivity and not so much our high frequency sensitivity. That's going to remain the same. And then finally, we have doing the Bayesian noise analysis in practice and how we model all these different sources of noise to our TOAs and our residuals directly. So I'm going to actually talk a little bit about the PTA sensitivity effects, and then I'll mostly move on to how we actually do the noise analyses for the rest of the presentation. And so one of the pieces of our model, so we can kind of reduce all of these different sources of noise I talked about earlier into whether it belongs in the timing model or whether it belongs into either a red noise or a white noise model or some additional chromatic model that we throw in. So the timing model is itself a source of noise, even though we do model it deterministically because we still have uncertainties in these parameters at the time of our gravitational wave analyses. And so we see the different types of timing residuals that we might get from errors in the individual timing model components here, where the top set of signals are mostly pulsar binary effects. And then we have a set of sinusoidal signals that have roughly a annual, that have roughly a frequency of 1/a year, just from pulsar proper motion and position and parallax errors. And then there's the pulsar spin down itself, introduces these linear and quadratic trends. And these each together work to reduce our sensitivity to gravitational waves, producing these different features we see on the right-hand side in our sensitivity curves. So the spin down effects are producing this low frequency increase that really kicks in once we get below a frequency of the observation time span of our pulsar. And then this 1/a year spike that we always see in our sensitivity curves is from the pulsar position and proper motion errors. Parallax always causes a insensitivity at 1/2 years, or sorry, 2/a year, because it's twice the frequency. And then we can get, these insensitivities at higher frequencies due to the binary orbital effects. If any of these effects are not accounted for in a proper way in the actual timing model, though, then they would produce some type of spurious signal at each of these frequencies, respectively. Alongside that, then there's the effect of different types of noise. So I kind of talked about this before, but in terms of the sensitivity curves, we always have some white noise floor, which when you translate from the space of power spectral density to characteristic strain, this produces this high frequency slope that scales as the frequency squared. And then we have our low frequency increase, just that's mostly due to the timing model itself, those fits for the spin frequency and the spin frequency derivative of the pulsar. And then as soon as we add any red noise or a gravitational wave background, that's going to increase this low frequency floor by some amount. It could be much larger in individual pulsars that have large intrinsic red noise, but at some level, there's always going to be this low frequency floor due to the gravitational wave background that we have to deal with, which will be a problem for continuous wave searches. And then finally, we also have what's the effect of these, for example, dispersion measure modeling on pulsar timing array sensitivity curve. And what I have here on the left, this is a plot from Jeff's 2019 sensitivity curves paper. This is showing a transmission function, which is, you can kind of think of as like flipping over the sensitivity curve. It's just showing how much gravitational wave power is actually allowed to be filtered through as a function of frequency. So if the transmission function is 1, then you have your gravitational wave power is completely unfiltered. And then any factor less than that is indicating that the timing model is filtering gravitational wave power at those frequencies. And these two curves are comparing before and after we include dispersion measure modeling via the DMX components in the timing model. And what we see is that the transmission functions are, or the blue transmission function is almost just a step decrease over the orange transmission function. And this is indicating that our dispersion measure models are reducing our sensitivity by roughly a factor of a third across frequencies. And so that's kind of, it's impacting both the low and the high frequencies at the same time. And on one hand, this could just be what we have to deal with when we have to model dispersion measure in general. But if we compare different types of dispersion measure models, so for example, this is from 2025 paper on optimizing the Meerkat pulsar timing array, but this is comparing sensitivity curves, whether we use the DMX model versus when we use this Gaussian process model for DM, which is the purple sensitivity curve. And in this case, by not including dispersion measure in the timing model, if we include it in the noise model and we use a more constrained prior on these dispersion measure components, then we can have much less power being absorbed by the dispersion measure model and get better PTA sensitivity. So on one hand, dispersion measure is always going to cause some insensitivity across the PTA, across frequency, but depending on how we model it, we can reduce how much sensitivity we're losing due to these chromatic effects. Okay, so those are kind of in the sensitivity curve domain, how things are looking. But now we should jump to the actual data analysis problem. How are we fitting all of these different types of effects to our timing residuals, which we have an example here on the bottom right, these of some timing residuals for pulsar J1600, where these different colors here are indicating different radio frequencies. And we can see some pretty dominant and clear trend in here. So there's definitely some chromatic noise we have to mitigate. And so what we want to do is we want to take all of these different noise sources and write down some functional forms for these different types of noise in terms of the achromatic noise and the chromatic noise, such as the dispersion measure variations. And we'll have these multiple models together that we fit. And so we'll usually, in practice for all of our analyses, we treat these as Gaussian processes. I assume you guys would have heard about Gaussian processes earlier in the school. I can give a quick recap on one way to think about it. So we have our Bayes theorem, right? And we have, when we're modeling our data, if we treat it as some set of functions that each have an amplitude, so this is what we see on the right-hand side. One way to treat a Gaussian process is to say that the parameters of our function on the right-hand side, which are these theta j, that are scaling some set of functions we know. If we give each of these parameters a Gaussian prior, then this is an example of how you can set up a Gaussian process. And having Gaussian priors on these linear model parameters is really nice because we can do a lot of really clean linear algebra with these. So for example, if we're using a Gaussian likelihood, we have a Gaussian prior on top of that, then we have a Gaussian posterior. We can do a lot of things with that in terms of being able to reconstruct our signals in the timing in the time domain and create some nice clean whitened residuals. It also means that we can analytically marginalize or integrate over these priors and be able to create some models which have a much reduced number of parameters. So this is probably more clear with an example. So for example, when we model red noise or a gravitational wave background, we'll treat this using some truncated Fourier basis, where we just go from the fundamental frequency 1 over our observation time span up to some finite number of Fourier modes that we choose to model. And we have, if we just fit this unconstrained to the PTA data set, we'd have these individual Fourier coefficients that we have to fit for. But we usually set some prior on these Fourier coefficients. We expect them to have a mean of 0, and if we're treating them as a Gaussian, they will have just some variance on top of that we can set. And we usually set that variance to be just have a power law form. That's one example of a way we could do it. We could also have each individual frequency have its own parameter for the total amount of power at each frequency. That would be the free spectrum. I forgot to include the Kronecker delta here if we want to assume that these the power at each frequency is independent of each other, but there's actually methods that exist now to account for correlations between frequencies using the Prometheus package. And in any case, what this would look like is in terms of our actual prior over each Fourier coefficient, we would get the variance is would look something like this for a particular power law form with an amplitude A and spectral index gamma. We'll have more power at the low frequencies, less at the higher frequencies. And in the end, we can just marginalize over all of these Fourier coefficients using by just integrating analytically these Gaussian priors and then just fit for the amplitude and spectral index. And so this whole process should sound hopefully very familiar in the context of gravitational wave background modeling. We're really doing the exact same thing for the noise modeling as well, just with additional terms that are intrinsic to each pulsar. And they do not necessarily have to have a power law spectrum. We could use a free spectrum. They don't have to use a Fourier basis. We can come up with some other type of basis for the individual noise process, and they don't have to be achromatic. We could add some radio frequency dependence on top of this. But this whole Gaussian process paradigm is the way that we usually account for these different types of signals. And so what is this? Let's start looking at some examples of noise models and how these different processes look like in the time domain. And so for our standard noise models that we use in Nanograv and that I was talking about before, so we'll always include red noise in the individual pulsars, achromatic red noise. And this could account for our intrinsic spin variations or orbital variations, but anything in general, regardless of what is actually in the data, we always want to model some achromatic red noise in the individual pulsars because the gravitational wave background is also a red noise process. And if we don't include the intrinsic red noise in the pulsars, then we run the risk of having any intrinsic signal that might be in there leaking into the gravitational wave background process. So that's kind of the conservative thing we always want to do is to include red noise. Here is a visualization of a DMX time series that we talked about before. And so these are included in the timing model. And this is a visualization of the parameters of each of the DMX parameters in the timing model, but they're, again, each a parameter that's fit at these different observations. And so you can create the time series out of them and compare that to our intrinsic red noise time series, for example. And so each of these, in total, we get hundreds of, even though we don't actually sample anything during the MCMC with DMX, we have hundreds of parameters that are getting marginalized over still in the model. And then on top of these, we also have our white noise models which are generally, we give them a prior that is time uncorrelated. So just a separate, just treating it as, for example, a Gaussian, each timing residual might have some offset that is just fit as a Gaussian distribution across the whole observation time span. And we assume that is going to be uncorrelated, but in reality, our white noise models can absorb some power that might be slightly time correlated. And so we can kind of see this in this time series here that's in the blue. And then our remaining timing model variations, we also include at the same time. And so just the timing model, the white noise, the red noise, that's all we usually have to include with this standard noise model. I would like to talk a bit more about the dispersion measure variations, though, because, and just what a pronounced effect they could be, because it really is a very dominant source of noise in certain pulsars, especially if you convert these, the effect of the dispersion measure variations into a timing residual, right? So what we have on this plot is just the total timing residual in microseconds, and the dispersion measure parameters are now converted into time delays at the different radio frequencies. So we have the lowest band, 800 megahertz, is in red, and then the higher bands at 1400 and 2000 megahertz are in green and in blue. And then that little black squiggle at the bottom there is actually the red noise time series from the last slide that we measure in this pulsar. So this is extremely, extremely quiet in comparison to the dispersion measure noise. And you can imagine how if we have any tiny errors in our estimation of this dispersion measure time series, how that might impact our red noise that we're trying to measure that's underlying this. And so this is kind of a useful visual to see why dispersion measure modeling is important to get right and why we should scrutinize how we're doing that a little bit more closely, which is what we're going to do next. So there's this other paradigm of modeling dispersion measure variations. Instead of using these timing model parameters, we can just treat them as these red noise processes in the noise analysis, the same as we do for achromatic red noise, but now they'll have some, we'll include that 1 over radio frequency squared scaling. And in general, we might have to use a more complicated model than just a simple power law, because the dispersion measure time series are can have a lot of different complicated effects going on. And also we can resolve any of these deviations from just a power law form very precisely because of how well we can measure these dispersion measure variations. So I've seen some dispersion measure models that have up to 9 hyperparameters once you're accounting for the interstellar medium and also the solar wind. But usually they don't. Usually you will use just the power law form for dispersion measure variations. And so to kind of break it down a little bit, if we want to use this DMGP model, right, instead of DMX, it will basically be decomposed into one piece, which is just going to be this power law red noise. And that is the exact same as the previous power law red noise. Again, we just have this 1 over radio frequency squared time dependence that we're including in here. And this is also actually expected for the interstellar medium if it is described by say just a model for Kolmogorov turbulence in terms of the variations in the electron density over space, just as the pulsar line of sight moves through that, then we expect to get a spectral index that is around 8/3 and having that power law form as well. So this is actually a pretty good model to use for interstellar dispersion. We also have a quadratic trend that we will want to include in the timing model. And this is for the same reasons that we would want to include these terms in the achromatic noise model, our frequencies, our pulsar frequency and frequency derivative terms, because this will help to uh, account for any of these trends that are below just one of our observation time span. And so it allows our finite Fourier series that we're using for the red noise to um, uh, be just modeling the stationary component of the noise and not be using a stationary model to model something that's non-stationary. So we always try to include a quadratic trend for that reason. And then finally, there's also this solar wind component that I was talking about before. And so the solar wind will, in terms of a DM time series, produce these spikes, and these will reoccur at exactly 1 year intervals, where the spikes correspond to where the pulsar is closest on the sky to the sun. And this can be modeled to actually very good approximation. The solar wind itself as just having a electron density profile that is spherically symmetric, just with a 1/r² scaling, where r is just the distance of the specific spot in the solar wind to the sun. And then you integrate that spherical profile along the line of sight from the Earth to the pulsar, and you can get this solar wind time series. And so if we know what the solar wind electron density is at a particular point, and this spherical profile is correct, then we can actually model the solar wind deterministically based on the pulsar's position on the sky. Any good heliospheric physicist will tell you that this solar wind spherically symmetric profile is very much incorrect, but for the purpose of pulsar timing, it still seems to do us a pretty good job. And this effect is also going to be dependent on how close each pulsar is to the ecliptic latitude. So in some pulsars, we don't have to worry about it at all, but in some pulsars, it's going to be maybe even the dominant contributor of noise in the pulsar. And the other effect that we have to worry about that is in some sense a manifestation of this non-spherical symmetry is the fact that the solar wind electron density is going to vary over time. So in principle, we will want to include a stochastic component to the solar wind model, which I can talk about a little bit more later. Okay, so when we put all of these together in the end, though, we add them all up, and then we can get our final dispersion measure time series in terms of the Gaussian process model, and comparing with just when we use DMX parameters, we get very similar results in the end. And we see this across a variety of pulsars. You know, if you use DMX and you use DMGP, you do get consistent results between all of these different pulsars. So both models work well to measure dispersion variations. It's just the minute differences in these models will propagate some slight changes into the red noise measurements if the pulsar has a large enough dispersion measure variation. And that's just because of how strong the dispersion measure variations are compared to the red noise. And so all of this is true, assuming that we have only dispersive effects in the chromatic model. And also assuming that we have modeled the time correlations of the dispersion measure series correctly. We can see across these different pulsars that different pulsars can show a variety of different types of dispersion measure series. Some are have more dominant solar wind effects, such as 1744. Some have these more dominant linear and quadratic trends, like 1909. 0613 has a little bit of like an annual trend that is not necessarily this related to the solar wind. And then 1713 has actually maybe the weirdest dispersion measure series because there's these sudden drops. And if you study these more deeply, this kind of underlies some of what are the more complicated problems with these different types of dispersion measure models and why we need to include something else in the end. So looking more deeply at 1713, we're just going to look at the standard noise model dispersion measure series, which we see in the middle here, and then also the achromatic red noise. And the achromatic red noise in the pulsar, when we use this model, is shown in the top panel. And I have these vertical lines here to show these events where the dispersion measure just suddenly drops. And so the question is what's going on here? And it's worth just thinking about for a second. Looking at the achromatic red noise, this is a little bit of like tea leaf reading in terms of looking at the model, the different realizations of these signals. But to me, it looks very much like there is some fluctuations in the achromatic red noise that are happening at the same time as these dispersion measure drops, right? The first event, the achromatic red noise has a big peak right at the same time as this first event drops, as the first dispersion measure dropped. And then at the time of the second dispersion measure drop, there seems to be this, fluctuation that corresponds at the same time, right? So that could happen by coincidence, but what if it's not? So something that could affect something that could cause this type of effect is if if you have some type of chromatic effect and it's not 1 over radio frequency squared, right? What would happen if you have your radio frequency squared model and your achromatic model is you would need to get the best fit to your timing residuals, you have to have some combination of both of those at the same time. And that seems to be exactly what's going on here. And the interstellar medium is not it's not expected to just all of a sudden drop like this. It's expected to vary smoothly over time, right? So in any case, if you take these individual components and you decouple them from the dispersion measure model, say you use the DMGP model, and then you add on some just exponential dip, right? So this is what's been done in the literature for this pulsar, is these events look like all of a sudden you have a step function where it drops down and then there's some exponential recovery. And if we fit these to have this radio frequency dependence, that's not necessarily dispersion. If it could have some other type of radio frequency dependence, which we fit for using this chi parameter here, then we actually find that the best fit in the analysis is not that these are dispersive. And for this pulsar, we find the first event looks more like it has a steeper chromatic dependence than dispersion, more like frequency to the -3. And the second one is more like frequency to the -1. And the impact of including this type of model is we have now a very smooth dispersion measure series in the middle panel, more like what we would expect from the interstellar medium. And then the red noise is dramatically impacted. We don't see these fluctuations that seem to covary at the times of these events anymore. Instead, it's just smooth across the time of the event. And this is reflected in terms of the achromatic red noise parameters as well. So here we have in the orange contour, this is our amplitude and spectral index of this pulsar's achromatic red noise before modeling these events. And afterwards, we get the blue contours. So we get a pretty dramatic shift in terms of the amplitude being reduced and the spectral index broadening. And if we overlay where we measure the gravitational wave background, this is pretty much on top of this pulsar's achromatic red noise. So 1713 is definitely seeing the gravitational wave background in terms of its achromatic red noise is right at the level where some component of it should be the gravitational wave background. And so depending which model we use here, just for this pulsar alone is going to have some impact on our gravitational wave background measurements. So this is a pretty egregious example of where we might have these more complicated effects we have to account for. There's also this question of what is actually going on with these events, right? So what actually are these? And these have been studied in a variety of different contexts. But what's been found about these is that it's not just a overall shift to the TOA as a function of frequency, like what you would get from dispersion typically. We're actually seeing changes to the pulse profiles at the times of these different events. And this indicates that there's something more complicated going on than just interstellar dispersion, which could be either some type of complicated scattering or refraction or lensing effect in the ISM that happened to happen twice for this particular pulsar, or maybe it happens for more pulsars and we only saw it in this one because it happens to be a very sensitive pulsar. Or there's something going on in the pulsar's magnetosphere, some type of whatever that word is. I can't speak it right now. In terms of the pulsar's emission changing. And as of past the nanograph 15-year data set, that's kind of what we think is happening now because just looking at the pulse's profiles, this seems to have happened again, but in a more dramatic way even, where if we look at this right-hand side plot, there's these 3 columns, which are these different time slices of the pulsar's profile. And we see that the shape of the profile is pretty dramatically different at these different time slices. And this is going to cause major issues for our analyses. We usually assume we have the same pulse profile that we fit across the whole time span. So and if we do that, then we get these plots we see on the left. In the middle, this is the TOA residual that you get using our standard template fitting methods. And then below that is the change to the dispersion we get with these different template fitting methods. And these are at these different bands of the Green Bank telescope and with CHIME. And we see there's this, again, this huge change in the residuals, but it also depends on frequency in a really weird way. So we have the leftmost plot is showing this timing residual delay as a function of frequency right when the event happens. And it no longer even has this power law scaling. Seems to be the highest residual around 1800 megahertz. And instead of continuing to scale down, it actually turns over. And then we have less delay at the lowest frequencies. So this is very unlike really any type of other noise effects that we usually model. And it's now hypothesized more strongly that this is coming from a reconfiguration of the pulsar's magnetosphere. that would cause just a change in the shape of the emission that it then eventually relaxes back to something closer to what it was before. And so there's a lot of really rich pulsar physics to learn here, um, alongside the fact that we want to deal with this or we won't be able to use it to search for gravitational waves. And thankfully, there are now methods such as this paper that just came out by Shania Nichols um, that are promising to be able to mitigate these types of events in the pulse profile domain. And so we see the initial residuals on the left, and then doing a type of profile domain fitting over time. You can regenerate the TOAs and then eventually get residuals that look like they're much flatter and smoother. And then at this point, we should be able to go and use the other types of noise models we've been using, just such as these exponential events and our various GPs on top of this, and be able to get good timing precision with the pulsar again. So this is work that's ongoing with the 20-year data set now. The other really nasty effect that I want to talk about too is manifests in certain pulsars as well, not all the pulsars. So this is one pulsar J1903. This is a plot from the Nanograph 15-year data set. And this is a lot like the plot that I had before for 1713, just now instead we have the DMX time series in the top panel. And the middle and bottom panels are showing the full TOA residuals and then the averaged TOA residuals in the bottom. And this is with mitigating everything except for just the last component is achromatic red noise. And so the question is, there's clearly a lot of noise in the residuals, but what exactly is going on here? Because we can see that, again, there seems to be a very clear correlation between the trends we're seeing in the dispersion measure series and the trends we're seeing in the TOA residuals. So based on what we saw before, there's likely, again, some type of chromatic effect that is not just having an inverse radio frequency squared dependence, and it's causing both the achromatic and the dispersion measure series to try to work together to just get a slightly better fit to the data. But as a result, both the dispersion measure and the TOA residuals are getting biased. So what do we do about this, and what can be going on? So the main thing that we think is probably going on here is this scattering noise effect, especially because, so this pulsar I use as an example, J1903, has had a lot of independent measurements via scintillation that show it is very highly scattered. It's also very far distance away, so there's more ISM that each of the pulses has to pass through before it gets to the Earth. And I alluded to this earlier. We see this plot on the right. The main impact of scattering is to broaden the pulse profile. And so if we just have some scattering that's time independent, then we can just fit this out directly using our using frequency resolved pulse profiles, for example. But then if this is varying over time because the interstellar medium is changing and the line of sight through that interstellar medium is changing as the pulsar and the Earth are moving through the galaxy, then the amount of broadening that we get in this pulse profile is going to change over time, and that's going to, again, affect our TOA measurements. And so there's been a lot of work on how to model this properly. And there's various different, if you make different types of assumptions about the interstellar medium, what's the geometry of the ISM that's causing this scattering, and what's the shape of the pulse profile that's going through that interstellar medium, you can get some predictions for how this is going to impact your time of arrival. So one prediction is that you might have a radio frequency scaling that's roughly the inverse of the radio frequency to the fourth power instead of the second power. And this is if you just have a thin screen assumption. If you have a Kolmogorov medium, this changes slightly to a frequency to the minus 4.4. But that said, there's many assumptions that can and do get violated that go into this prediction. So in practice, what we do is if we think there might be scattering in the pulsar, we fit an additional process that goes as frequency to the minus some value that we fit for during the analysis. And so let's see how this works for 1903, for example. And so if we include this model alongside, if we include this scattering model, which really we call it a free chromatic model, having this free chromatic index chi here, we can fit this alongside our DMGP and our red noise and see what happens. And so now we have this dispersion measure series on the top, the free chromatic noise in the middle, and we have the achromatic red noise on the bottom. And we can see that there's a very strongly measured free chromatic noise in here, right? Some pulsars, you might fit this model and you'll just get completely flat posteriors that just lie around zero. In this case, there's clearly some trends that are getting picked up. And there's a couple spots that I've circled in here in the green time series that seem to correspond to some of the trends in the original plot on the upper right. So for example, that this kind of bump towards the end of the time series does seem to get picked up in this free chromatic noise. And it's no longer seen so much in the dispersion measure in the red noise time series. But at the same time, some of these anti-correlations between the red noise and the dispersion measure still seem to be present, even after including this model. So what could be going on? Maybe this pulsar really does just have coincidentally some variations that are happening in the dispersion measure and just the intrinsic like spin noise or orbital noise at the same time. And there could be some explanations for that. Or perhaps just our chromatic model is not quite accounting for all of the scattering correctly, which is probably the case. If we look at using this free chromatic noise model across a bunch of different pulsars, so we did this with the nanograph 15-year data set, for example. We get these different blue posteriors here in this panel for different pulsars. And then there's a few other points on here which are showing these chromatic index measurements for the scattering from other PTAs as well. The NPTA DR2, MPTA DR2, and EPTA DR2 low, which includes LOFAR. And some of the measurements are consistent with each other, but a lot of them are quite inconsistent with each other, even across different PTAs. 1713, for example, shows a lot of different values for this measurement. So the fact that there's these discrepancies shows that there's some level of mismodeling that's still happening. And furthermore, there's also this great paper recently using simulations to test the current models that are in use for scattering variations. And so, for example, this top plot here is showing this centroid signal, which is really like a simulated residual due to scattering. Whereas the bottom panel shows what you might get just from a Gaussian process model. And qualitatively, the signals are quite different because the centroid signal tends to be a little bit more peaky and have these spikes that show up, which would be representative of some type of non-zero skewness in the model, for example. That is not picked up very well when we use a Gaussian model. And they argue that some of the discrepancies we see in the or some of the strange values we get for the chromatic index are an artifact of not having of the scattering truly being non-Gaussian. There's also this middle panel here is a correlation coefficient of the scattering signal with itself at different radio frequencies for different simulated types of scattering screens. And this shows that if this was just a line at the top, correlation coefficient of 1, that would mean our scattering signal is going to have the same time dependence across all radio frequencies. But the fact that in many of these panels, it dips down to smaller values shows that the scattering actually decorrelates as a function of radio frequency. So one thing that we'll need to do in the future is account for these potentially decorrelating scattering signals. And a way to think about that would be, to take one of these GP time series and kind of morph the shape of the time series as a function of radio frequency. And we do thankfully have some models that are capable of doing this. Okay, so and then the last thing I'll mention about scattering, and then I'll kind of wrap up because I think we're running low on time, is that the best way to deal with this in the end is likely going to be the same as with those 1713 events, which is dealing with these events in the profile domain. Because we know that or we can treat scattering as essentially this convolution between the intrinsic profile of the pulse and some pulse broadening function that comes from just the physics of the interstellar medium. And when you convolve those together, you get your final pulse profile. The thing is, the intrinsic pulse should not be changing except just due to purely dispersion and achromatic noise. And any of these pulsar magnetospheric effects. But then the pulse broadening function is going to vary due to the interstellar medium. But if at the time of the TOA generation, if we can have a good way to deconvolve this pulse broadening function from the intrinsic signal, then we can mitigate the scattering before we even get to the timing residual, which is the goal of certain algorithms that have been developed within the noise budget working group, such as there's a clean deconvolution algorithm developed by Olivia Young and Michael Lamb, or used for this PTA scattering mitigation context specifically. And then there's also work on being able to do this deconvolution automatically just with the baseband data that we get at the telescope using this method of cyclic spectroscopy, which I am not super well qualified to give a lot of details about how it works. It's kind of like magic. But you're able to use the phase information of just within the baseband data you get of your pulsar measurement to be able to deconvolve this pulse broadening from your intrinsic signal. And so that seems like a very promising method for these very highly scattered pulsars, such as 1903 that we saw. And then we'll hopefully not see as much of these weird results in terms of our scattering chromatic noise as I've been showing. Okay, so I know we're running a bit lower on time now. I have a bit more I could talk about, but I think it would be good to stop here to see what questions people may have about what I've talked about so far. and we could just kind of have discussion the rest of the time, unless people have also more questions about anything I haven't talked about yet as well.
Hi, Bjorn. Can you hear me?
Yep.
I may have missed this, but can you talk about why you include the quadratic term on the DM, like the DM modeling? Like you include the kind of red noise DM and then the solar wind, and then there was a quadratic term.
Yeah. So there's yeah, I didn't explain that very well. So thank you for giving me a second opportunity to try to explain that. Um, I should say there's kind of two reasons to include that. So one is that we actually do expect to get like a very strong, like linear and then also maybe quadratic dependence in a lot of DM variation series. Specifically just from a lot of pulsars will have some component of the will have some strong component of the motion that's either towards or away from the Earth. And so if you just think of like the pulsar moving away from the Earth over time, the distance between the Earth and pulsar is getting larger. And so there will be more free electrons just in between the Earth and the pulsar over time. So that will just cause some linear trend in the DM series. But then in terms of the actual, like when we do this modeling with this truncated Fourier basis and we use this power law spectrum, it's, because we're kind of cutting off the series at just the inverse of the observation time span, it's better to include this, some type of quadratic trend or some additional set of like logarithmically spaced frequencies below that observation time span, because otherwise you will not have, you can have like it's basically like the spectral leakage effect between uh, between frequencies will get a lot worse just from our uh, TOAs not being evenly measured. So it's part of the problem of using a Fourier basis, or using a Fourier series to model like non-evenly spaced data.
Yeah.
Yeah, and
And
there. Oh yeah, were you gonna
well,
say?
I was just double checking. So this quadratic component is taking care of the fact that the pulsar is likely going to be moving away or toward the Earth just due to galactic, like accelerations or rotations, I guess.
Yeah, that's like the physical reason why we would get like these
But
ultra low
it
frequency
gets difficult
trends.
in the Fourier domain, which is why you have to do it quadratically.
Yeah, I mean, it's not like you have to do it quadratically. There's some pulsars that not wouldn't necessarily need it, but it's better to use it because at least like just in my experience, I've tried using just the power law model by itself without including the quadratic trend, and it's going to it's going to try to work really hard to like try to model the quadratic trend and also the smaller fluctuations that are underneath there at the same time. And it's much less likely to be a good fit with like just a power law spectrum.
Okay, thanks.
Hi Bjorn, it's me again. I have a few, and I'm also very happy to move these off of Slack if it's going to take too much time. First of all, follow up to Levi's question. If the quadratic variation was only due to the pulsar moving as a result of the galaxy moving, wouldn't that be lumped into the proper motion term in the timing model?
Yeah, so the proper motion term is dealing with yeah, the problem is the proper motion term of the timing model is going to introduce some they are dealing with different effects. So the timing model effect is dealing with the um, fact that we'll have some error in the actual pulsar position on the sky over time. And if that error continues to propagate as the pulsar moves further and further away, we will get that annual trend from the basically just having a different, assuming a different line of sight from the Earth to the pulsar, getting this error from the Earth moving around the sun over time. It's just, so the proper motion timing model effect is just accounting for time change in the pulsar position annual error that you get.
Okay.
Whereas the ISM effects are not accounted for in that timing model component.
Okay. Then on to some of my other questions. One of the things I was very interested in that you were saying is that when you were dealing with these like pulse profile events and when you did a what was this custom dip model, right? It looked like on the contour plot that had a very large spread in comparison to the not having a custom dip model, which is interesting in its own right that we seem to have a more constrained area when we are just using the standard model. So that is interesting, and I might talk to you a bit more about that later. But when you do more of this custom noise modeling to kind of account for these pulse profile changes, do you see that lower sensitivity to the gravitational wave background occur all the time?
Okay, wait, let me try to rephrase your question just to make sure I understand it. So you're asking if we always get lower gravitational wave sensitivity when we are using custom noise models, or like lower gravitational wave amplitude measurements is maybe
Yes,
what you're referring to in this case. Yeah, so that's not necessarily the case. I mean, especially custom noise model is like a term used very loosely just to mean like it's a model that's individually tailored to the pulsar because we won't have these types of events that we see in all the pulsars. In general, but I think in general, your intuition is correct though, because if you have some type of delay that is um, incorrectly mitigated in a way that is actually measurable in the data, and especially if it's chromatic, what then happens, like if it does not have a dedicated channel in the model, such as these individual dip events, then it will just go into, whatever combination of all the other noise models we have that best fit the data. So it will go into some combination of dispersion measure, red noise, and white noise, and potentially the gravitational wave background too. So if you have a red noise signal that's like as or if you have a pulsar that sees the gravitational wave background as well as J1713 does. And so just in general, having that unmitigated signal will, add some amount of additional noise into the signal we're trying to model. But there's also ways in which I mean, I have to think about this more. I think there could be ways to artificially um, you know, it is possible just in like this type of data analysis problem to include too many signals or have specifically like a signal that has overly um, a signal, a noise process with too large of a prior could introduce some more support for putting your gravitational waves background signal into the noise process. And then that would produce some overly low amplitude measurement than the actual signal that's intrinsically there. Yeah, I guess your specific question, does the red noise amplitude always go down though? It can go up to, so for example, if you include a model for scattering noise in the pulsar because you think that might be happening and the scattering noise is not really that easy to measure, then you could get some covariance between the red noise and the dispersion measure and the scattering in terms of the amplitude parameters. And that will cause your red noise amplitude to increase just because there's more flexibility in the model.
About red noise, are you talking about all red noise or chromatic or achromatic red noise here?
So I'm talking about all red noise. Actually, I have a plot towards the end that shows an example of this. In the context of data combination. So there's this is comparing different. So we have chromatic noise on the left, and then dispersion model, or dispersion measure parameters in the middle, and then red noise on the right. And these blue and orange contours are comparing if you have more versus less data that is in your total pulsar data set. So this is in the context of like IPTA data combination. But you can see that, for example, if you're, you know, uh, if you have less constraining data, your red noise amplitude as a whole is much less constrained and can be at a much higher amplitude than if you have more constraining data that's included. And part of this is because we have some covariance between these different noise processes, this red noise and this dispersion measure and the chromatic noise.
Is that due to what you were hinting at earlier, that there's some like leakage between some of the other noise processes? Like there could be like chromatic components to jitter possibly, or the magnetosphere events could also possibly behave chromatically as well as achromatically.
Yeah, that is also a factor in there too, right?
Because
And
that's an additional factor, and as well as that there's just covariance between these chromatic noise processes as well.
it's an additional factor. And I mean, there's two different types of covariance that um, I've kind of alluded to. So there's the covariance between the hyperparameters of the model. So you could have, your dispersion measure amplitude and your red noise amplitude could be covariant with each other because your data are not able to sufficiently resolve one process from another. And then you could have covariance in the posteriors of your different time series for the red noise and the dispersion measure, and that would occur due to not having due to having some chromatic mismodeling or something such as a frequency dependent jitter or some scattering that it's not completely accounted for well by the white noise model. So it goes into some combination of the red noise and dispersion measure models too. Um, and so these all of these dynamics are happening potentially at the same time. Um, yeah. Does that answer your question?
It gives me a few more, but I'm gonna slack you and pick your brain there.
Yeah, we should definitely chat more.
Yeah. Is the are you in the VIPER Slack or should I hit you up on the Nanograph Slack?
I'm in the VIPER Slack, and anybody should please feel free to follow up with me more about this. And I can also share resources to read more about these kind of different problems in noise modeling as well.
Yeah, okay. Thank you so much, Gwen.
All right, do you have any more questions for Bjorn? Thanks for right now. Bjorn, you're pretty much wrapped up at this point, yeah?
Yep. I mean, I don't want to go into the break time. But so yeah. But if anybody has more questions, I'd be happy to chat more.
Yeah, let's put more questions for Bjorn on the Slack, and I'm sure if there are more slides you didn't get through, Bjorn, then people can check through those later if you can
Yeah.
upload them.
Yeah, so there are definitely more slides, and I will have those uploaded onto the VIPER GitHub. And so, yeah, everyone should
Amazing.
check those.
Thank you very much again, Bjorn, and let's give him a round of applause. Alrighty, so let's take our morning break, and we'll come back at 11:30 with continuous wave descriptions from Matt. Right, so simplest thing is probably just to join the Zoom. Yep. And then share screen. I'll stay here and make sure that.
Sweet, yeah. Curtin's gonna, Kevin's joined. They're gonna help out with like questions and stuff as well. You might get the occasional question given you wrote the slides. We'll see how it happens. Audio through this computer, I imagine. Not now.
Yeah, that's right. Getting dropped off.
Do I share position? Yeah.
Sharing the entire screen.
No, I'd really not see. Does that give me presenter view?
Try. What about,
Or do I have to go into presenter view first?
yeah, maybe share the presentation first before you go into the presenter view.
Oh, sorry.
Share. Share your presentation. And now the.
Let me see if I can just, I'll jump into presenter view and I'll see if I can share the screen that is not the presenter view screen.
Actually,
Yep.
X out of that. And go up here. That's like. Click out of it. There was another icon up there.
Does it only appear when I'm doing this?
It's like an option about whether you treat that as a screen extension or not.
Jason also?
Screen mirroring.
Let's see.
Yeah.
Do that. And then go, yeah, sweet.
Amazing.
Cool.
Fantastic, all right. If you're just finishing your snack in the morning, we're going to pivot quite strongly now from noise to signal. We haven't really talked too much about signals from individually resolvable supermassive black hole binaries, but that's what the lecture this morning is going to be about from Matt, and then the tutorial later after lunch as well. Matt is a postdoctoral researcher here at Vanderbilt, and he originally hails from Australia, where he was at Swinburne University, working with Brian Shannon, Daniel Weird, Matt Bales. He's done tons of analyses for the Meerkat pulsar timing array, which had some fantastic results just a year or two ago, showing complementary evidence for the gravitational wave background. And now we're moving on to individual sources, which Matt's going to tell us all about. So let's give him a round of applause.
Great, thanks for having me. So this is actually, so Caitlin Witt is also involved in this presentation. They're going to be helping me out with some questions at the end. I'm fast becoming very good at this subject, but I'm still kind of learning. So it's a bit of a trade between us all. So yeah, Steve said, my name's Matt. I work here. It's been great so far, but originally from Australia. Today I'm going to tell you about continuous gravitational waves, which I suppose is a little bit different than the stochastic version. I like to think of it as sort of like a more simpler, intuitive version, but we're going to quickly learn that it isn't. And so be very excited for that. Let's see, will it let me? There you go. My cool animations aren't working, which is just terrible, but we're going to go through 4 major parts of this presentation today. So we're going to start with the source. We're going to talk a little bit about what is creating these continuous gravitational waves. Then we're going to go into the waveform, and I've got a little notebook here that I'll be writing down the derivations with you, so I don't go too fast and everything, but the slides will also be up after the fact, so we can discuss them later, also on Slack if there's any issues with it. We're going to talk about how the pulsar actually responds to a continuous gravitational wave, a discrete source rather than a stochastic background, and then a little bit about searching. And I'm only doing a little bit about searching because in the tutorial directly after lunch, we're going to be basically going through the main and fast-ish pipelines that we have to search for continuous gravitational wave signals. And in that tutorial as well, the first part of it, there's a little scrap together notebook of how you can actually make your own simulated data. So we'll make our own simulated data, then we'll go try to search for signals, try to understand why it's difficult or why parts of it are easy. That's for you to decide at the end. Such a shame. So the source is supermassive black hole binaries, and I put it probably there because who knows? I think we all kind of think it's probably a supermassive black hole binary universe that we live in, but there's plenty of research to suggest that that isn't the case. There's lots of other options that could be creating the gravitational wave background signal that we see, but we think that it's probably built from things like supermassive black hole binaries. So I've got some GIFs here, and I can just tell they're not going to work. How much this is janking around. But this is a representation of a background. You know, this shaky image we're seeing here. We've got a lovely couple of. Okay, this is a laser pointer. Is that working? Oh yeah. So we've got a lovely couple of supermassive black hole binaries here, and the universe is spinning at a frame rate, which isn't usually what happens. But we've got the Earth here, we've got some pulsars all around, and this is so the fabric that you can see here that is much nicer when the GIF is smooth, is how I tend to imagine the gravitational wave background that we now have rather strong evidence for. This graphic was made by Carl Knox, who's a graphic designer down in Australia. He's very, very good at his job. But what I think is somewhat more interesting is this other GIF, which you also can't see properly, which is 2 supermassive black holes like directly relating to each other. So how, rather than the incoherent superposition of many nanohertz gravitational wave signals, one of the next things that we want to be looking for is trying to see they're discrete signals from just like two supermassive black holes that are binaries that are orbiting each other. So this is a simulation from NASA, hydrodynamic simulation. And if you could see the GIF, you would see two black holes orbiting each other and pushing some stuff around, which is kind of meant to be the quadrupolar emission of the gravitational wave. And the reason why I think we want to be pursuing this now, I don't have that plugged in, that's why it didn't work. Come on. It's going to work, yes. So why we care about this is rather simple, to me at least, because a continuous wave, a direct source, is a real object. So it's not a statistic, and the statistics are very important. The statistics, the amplitude and spectral index that we find give you the sort of like, the cosmic merger history of galaxies, and that's fantastic, that's awesome. But to get an actual astrophysical object out of this astrophysical science is also very important. We get very real astrophysical numbers that we have very shaky bounds on at the moment. Things like chirp mass and the orbital frequency or sky position isn't something we have shaky bounds on. We don't know where they are. We have no bounds on them, really. And one of the most important things is that we can actually go and look at it. So ideally, what's going to happen is we will find a continuous wave in our data. And then we're going to get some sky localization area out of that. And we're going to be able to go look at that sky localization area, and we can hopefully pinpoint where it is. Now, many people will tell you that we won't be able to do that. Because I think a lot of the research says that that sky localization area we're going to get is going to be so unbelievably broad. There's going to be so many potential candidates that you're going to be able to fit in there. That's great, Steve. It's just huge. But benefit of looking to the future very optimistically, I might be wrong. We might be able to see it very easily. It might be a very strong electromagnetic signature that fits into our sky localization area and fits to our orbital period, our frequency that we detect, and we can find something very interesting about the universe that hasn't been found just yet. It also might tell us what the driving force behind the in-spiral is. So I put a little question mark there because I wrote this down, and I remember the conversation I had that the final parsec problem might have basically been solved now and no one's really concerned about it. I don't know that. I don't know if that's directly true, and the person who told me isn't actually in the room, so I can't quiz them about it. But I think it still gives us a sort of a bit of information and a solution of what is driving that final in-spiral as the black holes get within a parsec of each other and start to actually in-spiral into a chirp eventually. And if the pulsar term cooperates, we hopefully might be able to read the evolution through time. So this is going into our derivation that we're going to go through a little bit later, that the same gravitational wave source hits the pulsars and then hits us, or other way around sometimes. But we are looking sort of in the past at these pulsar terms, and we're seeing how the gravitational wave evolved many thousands of years ago to us. So we should be able to read the evolution of the chirp of a supermassive black hole binary, because the frequency would change very, quite a lot over the thousands of years between that signal hitting the pulsar and then hitting us here at Earth. And the final point I'd make is, the background is probably made of these, and it's the next milestone. And again, probably, because if there's anybody in the room that really enjoys anisotropic backgrounds, they're going to argue with me. But I would argue that finding continuous waves and single sources is just a piece of the puzzle that anisotropy kind of fits into. Okay, so the waveform. We're going to start very simply, and it's basically just Kepler's equations. This is a very nice, simple explanation that I've ripped out of Steve's notes. These the notes that I'm presenting now are very heavily inspired by Sarah Vigeland and Steve Taylor here. So any questions that if you feel my answer is unsatisfactory, we have another lecture, which can work out quite well. But all of this is basically, all of this can sort of be related very simply to just how Kepler's laws work, how two bodies that are orbiting each other work, and how we try to interpret it. So we have, I'll write this down with you actually, so that I know that I'm not going too fast. But so we know we have a system with two masses in it, and we're going to call that big M, which is M1 plus M2. And then we want to relate that system so that it turns from a two-body problem into basically a one-body problem. And we do that by relating the masses together under this total mass and reduced mass formation. So this circle up here that we've got in the top right, if you can see that, is that, I've got two cursors. No, that's second, oh, it's here. Okay, never mind. This is the total mass, this primary mass that we're putting in the middle there. The A is the separation between them. The mu there is what we call the reduced mass, which is how we're going to couple these things together so we can turn it from a two-body problem into a single-body problem. And there should be an omega just next to this line here, which is the orbital angular velocity. So here we go. So we have a lot of information out of this just already from a very, very simple two-body problem that's going to be interacting with itself. But we have something in there we just don't want to deal with. We can't get any information out of. So instead, what we want to do is we want to get rid of A, and we want to just try to solve these equations in terms of just the mass and the orbital velocity, because that's going to be ultimately the information that we have when we start thinking about these things in terms of two supermassive black holes in emission. So just like this. To get nanohertz waves, yes. So I think when you start getting the extreme mass ratios, then it moves into millihertz. Is it microhertz or millihertz? Millihertz, yeah. So that's something called emeries. They're called extreme mass ratio inspirals. Those are going to be a very, very big deal and big problem for LISA, or an exciting data analysis challenge, as we call problems in physics. And I think that they're going to have to try to find very, very complicated waveforms to deal with that. But in the nanohertz regime, they're going to be both supermassive black holes. So very, very heavy to get that lever arm, which creates the very powerful gravitational waves. So this substitution here is very simple. It's going to draw our attention to it again because we're going to use it everywhere. This comes up about 3 more times in this talk. This is the most key thing, and it's just Kepler's third law. Kepler's third law is the most important thing in supermassive black hole binary physics. He was ahead of his time. Or I don't actually know who Kepler is. It was Johann? Johannes. But you know, if we try to put some numbers around this, I just have this in my sort of lecture notes. If you take these numbers that we have here and we put like a 10 to the 9 solar mass, like total solar mass in here, and then we put in something like a 10 nanohertz wave. And so the angular orbital velocity we have here is 2 pi f, which f is the frequency of the gravitational wave, or frequency of the orbit rather. Then we get a separation out of it, which is that A, which is on the order of a few hundredths of a parsec. So this is just sort of just, I'm just trying to use that to describe that when we get to this regime that PTAs are sensitive to, we're always looking at a portion of physics where we're in the final combined state. We're in the final parsec problem already. So we've pushed through that regime. When supermassive black hole binaries start emitting gravitational waves, they're generally at milliparsec scales, so thousandth of a parsec. Steve, I just noticed the food is here. Okay. I just noticed the food is here. I've got a little bit left to go, as in like most of it. Yeah, you want to just take a break? Is that it?
Take a little break for lunch and then back for your stuff.
Yeah, sure. Yeah, I've got like an hour left, so I'll just or like half an hour, but yeah. Does that work? Oh yeah, right. And this is just a cheat sheet, so I just put some stuff there so you know where it is. We've got G there, and some of you may have said, "Oh, we're not using G." We are. I'm pretending I'm God here, and I'm saying G is 1. And that's the greatest thing you can do in physics. G equals C equals 1 is the only equation you should ever know, except for the other ones. So don't worry too much about it. But there is a gravitational wave constant here. It is included, but we can ignore it because we're physicists. It doesn't matter. So where are we going next? Let's have a look. Okay, so I believe Steve has probably been over this when you did when they did the derivation of how the antenna response function comes across for pulsars when it comes to the strain. So you covered the quadrupole moment, I assume?
Yeah, I covered.
Fantastic. So we already know from the get-go that the gravitational wave comes from the second derivative of this mass quadrupole, which is the IAJ up there. And so we've got the time that we receive, and we've got R there, which is the distance, and it's just sort of the retardation time from where we are towards the source. So if you take the second derivative of that quadrupole moment, suddenly you start getting the emission of gravitational waves, which is good because we have jobs. And if we start to take this very, very simply and move this very simple Kepler's equations of two masses orbiting each other now into the gravitational wave regime, we can just imagine that a circular orbit is defined in an xy plane as this, which is just some constant in front, and then cos phi, sine phi, and then 0. This is approximately, when you apply this into the moment, some equation of the form mu a squared cos 2 phi sine 2 phi. The only reason I'm putting this here rather than describing the big matrices is because the big matrices, I'm sure you've probably seen them before. If you haven't, I can link you some notes. But there's one very important thing to sort of remember about gravitational wave emission that's sort of kept in here. And it's the fact that it's 2 phi here, and it's not phi. And that's really interesting, because that means that the gravitational wave emission is actually not to the same order as the frequency. It's the order of double the frequency. So you can kind of imagine that, hopefully this sort of makes sense, is that with t is the orbital period of these two masses we have here on the left, we're swinging it around. Every half period, you get a full revolution of the gravitational wave. And it's because of that 2 phi thing that comes out of that. Now, the reason behind this is very interesting, because I looked this up yesterday, and it's because it's a spin-2 gauge. I'm not really great at that. So the intuitive reason that I have for you, which I like, and this might make Steve cringe, is if you imagine that this is a barbell, this two-mass system, and you start spinning it around, every 180 degrees, this becomes symmetric. And you can imagine that at every symmetry that you have, there is a push of gravitational waves that comes out. And so every 360 degrees, every full revolution, you're going to get two gravitational wave pushes out of it. And Steve, was that okay?
The fact that it's a symmetric mass distribution after each half period is, and the fact that it describes twice the orbital frequency, that's basically it.
Beautiful. Please.
When you have non-equal masses, derivatives both do the same or look the same, you have more of a extreme mass ratio, would we see a difference in amplitudes of the waveforms?
My impression is actually no, because the quadrupole only cares about the mass distribution and how it shifts. It's not about the individual masses. So if they're coupled already, if they're in spiraling, I don't think so. If you've got extreme mass ratios, I don't know, because I think the extreme mass ratio, like the millihertz band version, probably comes from the acceleration of the smaller mass, like very accelerated over the larger mass. But for things like nanohertz gravitational waves, I don't think so. Did you ever comment on that, Steve?
Yeah, it doesn't really matter. It depends on things like reduced mass and total mass.
Yeah.
That is reduced curve. It doesn't really matter whether Cat 1 or MCR.
But in the terms of the Emery, in the extreme mass ratio, is the gravitational wave there coming from the interaction of the two bodies, or is it coming from the smaller body chaotically moving around the larger body?
It's coming from the small body effect in the test mass.
Yeah.
The mass of the black hole.
Yeah.
And it is the two body like quadrupole moment, a very, very small thing, a very large thing, generating gravitational waves.
Okay.
But it's the comparison.
Okay, cool. Okay. Fantastic. Okay. All right, so if we plug what we've just found from H equations, and then we take, just going to quickly recollect where I was, sorry. There we go, we got the second moment in there, fantastic. So if we plug the second moment that we're evaluating for this binary in an XY plane into our H equations, then we can get our H plus and our H cross to come out to these forms here. And this just comes directly out of the moment tensor, the derivative, the second time derivative of the quadrupole moment. You just get this out of the tensor. So it just comes out in exact H cross and H plus form. So the important thing really for, as far as I'm concerned here, is that you just have this 2 phi term, which is sort of speeding things up. And this actually might be an okay place to break before we go on, or do you want me to finish this a little bit? I think it's about to dive into something else. So it's kind of like if we do this or, yeah.
So we come back and give them.
Yeah, it's fine for me. Yeah. Is that okay? You okay with it? Yeah. Caitlin, I don't know if you heard that, but we're just going to break for lunch because it arrived and we've got a bit left to go through. So we might be back at 1. That's okay.
Sounds good. I'll hang out.
Which is why you guys. This is a meeting. Things that like the. And then. Oh. Yeah, it's really, because of the political, medical issues, out there, and you're really not managing it, so that you have. I think the income tax system is very different now. So it's going to be so it was, I thought, very slightly back on the line, so they have imagining. But yeah, we said, it's If it looks the same, I told you, everybody has a year, that's not gonna work. No, like, I think that's.
Yeah,
They always won't be on their head, start back.
yeah, it's really, we can take, I mean, however much you want. I just noticed I didn't want Caitlin, are you online? Better.
All right, Martin's turns.
All right. Okay, how's that look? That's all right. Oh, good. Oh, it's an awesome. Okay, we're going to pick up from where we were. So now we're just sort of now going to combine a very basic understanding of Kepler's laws with a very basic understanding of gravitational waves. So the plus and cross modes of gravitational wave emission come out to these forms here. They come out from, sorry, I'm just trying to move the window. They come out from the evaluation of the second moment of the quadrupole, sorry, the second time derivative of the quadrupole moment. But you might notice here that we have this A term, and it's the one we really, really don't want. The A term is useless to us. And so what we're going to do is we're going to borrow some information from Kepler's, is that working?
Yeah, it's fine. Just wait it. This is a Zoom thing.
Oh. Okay, sweet. So we're going to borrow that same substitution we used earlier, and we're going to start getting rid of that A term by just putting it in terms of the mass and the orbital angular velocity. I think the reason we want to do this, obviously, is we just don't, when we're trying to look at a gravitational wave signal, when we look at this continuous wave signal, very little of the information is going to be given to us about the separation of the binary, really. We have the evolution of it, we've got like eventually the chirp, and so we'll be able to work it out from that. But beyond that, that's kind of a useless thing. So we want to do this separation to try to get a more comfortable way to interpret the masses going around each other. What a lot of people do, I think probably someone's already mentioned this, I imagine, is to, instead of using the total mass, which is m here, or the reduced mass itself, we're going to use the chirp mass, which is a combination of the two. So it's the way to take this form of this equation and only have a single mass product out of it. I kind of interpret the chirp mass as the gravitational wave emission mass, really. I think it's always used in papers and stuff. But I don't think it actually has a physical bound. I think it's sort of a convenient algebraic form. And if anyone knows better, please correct me on that. We've also got Q, which is the mass ratio, and this is how the mass ratio is interpreted with the total mass to get the chirp mass. We're actually not going to use the mass ratio again, but Q comes up in every single paper that you'll ever read, and so it's worth understanding what it is here. I think that's it. Oh yeah, cool. So then we take the equations that we have at the top, we do our little switcheroo, we get rid of that A, because the A is the worst thing that we've ever seen. And instead, we've got this lovely H plus and H cross representing the polarizations of the gravitational wave that are interpretable totally off of the chirp mass of the binary. So the physical parameters of the mass of the binary, the phase of the binary, the orbital frequency, and the distance to the source itself. So it's now nice and easy for us to interpret this in terms of a gravitational wave equation, which we've all become very intimate with over the past week or so. And my slides will not work again. Yep, cool. So what if we aren't lucky and we don't actually have it in the X and Y plane? What if there's some kind of inclination onto it? The good news is it's still very simple. So all you have to do is you have to rotate the equations so you're still in the frame of reference of the source. And so the rotation tensor just applies this 1 plus cos squared I term and cos I term here. And this is just saying that the I is the inclination. And so just rotating into the frame of the inclination. And I couldn't draw this in PowerPoint very well, so I've stolen it from Steve's notes. This is what it looks like here. So if we have the inclination angle, which is just this angle in between here, And this is the sort of like the face of the binary orientation. And this is where we're viewing it, the lovely eye over here that Steve's drawn. This is how we can interpret how the inclination angle comes into the equations here. So as the inclination is applied, the gravitational wave power in the polarizations is changed very slightly via this method. I couldn't work out how to do an eye in PowerPoint. Was the hardest bit.
Very easy to draw out.
Well, I kept doing circles, and then I did like the lip. So you can see this. I actually had like a sideways lambda. I tried to do a sideways lambda and put a circle in it. I'm like, oh, it'll look like an eye. It didn't. Nothing I could do looked like an eye. It's terrible. We're being joined. Brand new physicists. Sorry, just trying to get my train of thought in. Yeah, cool. Okay, so the next thing, what if it evolves? Can we find the phase? That is not a worry at all. We definitely can do that. That is very simple. We have this evolution of the orbital angular velocity just here, which is defined basically out of the gravitational wave luminosity. So we know if a binary is emitting gravitational waves, it must change over time. And so I put a little like note here. Imagine, if you will, that energy loss shrinks the orbit, and that's because it does. We don't really have to imagine. That's just truth. That's nice. We've got a solid bit of truth in gravitational wave science. But if you take the luminosity function and how the change in energy over time relates to it, you can eventually get out how the angular orbital velocity also relates to it. So it's a much longer-winded derivation. There's a set of slides by Sarah Vigeland that this slide deck is based off of. I'll link that to everybody as well because it's very good, but it's got multiple slides of how you get there specifically. But the easiest link is that you can link the change in the energy into the gravitational wave luminosity into eventually this equation down here. If we have, if we want to actually find the orbital angular velocity at any point, we just have to integrate this out, and that comes out to this form here. And if we integrate that again, we just get the phase. And the phase is basically just saying that it accumulates through time as the angular velocity changes, which kind of makes sense. Like if you're looking at the phase, how it changes through time, you've got the angular velocity, which is the actual orbital movement. Then you will sort of like, as you integrate it through time, you'll get the orbital phase as well. Anything specific I want to say here? No, I think this is okay. Move on to the next bit. Okay, so now we're going to briefly talk about how the pulsar actually responds, how it actually feels the wave. So we have now a relatively okay basis of how gravitational waves permeate the universe and how a binary will create a wave that we can interpret. But now we have to actually talk about what the pulsar is feeling and how we get to interpret it. So a millisecond pulsar, extraordinarily stable clock. And it's going to be basically just sitting inside that wave. We've got a pulsar some kiloparsecs away, and we've got the Earth right here. We're getting some kind of redshift between those two events. And so the redshift is interpretable as this. Well, the delta nu up here is the frequency of the wave of the Earth minus the pulsar over the frequency of the wave. And this redshift is interpreted directly as the antenna pattern, which I believe Steve would have gone over earlier, which is just a geometric factor versus the delta HA. Oh, did we get? We got someone. The delta HA here, which is the gravitational wave, the H impact we were talking about before, and the delta just represents the difference between it acting at the pulsar and at the Earth itself. So that's where that redshift lever is coming from. If you integrate this, oh, sorry, this is the same thing I just said. This is what delta HA expands out into. So time here at the Earth and minus the time at the pulsar. This is kind of important that there is some kind of difference between what's happening at the Earth and the pulsar, because you can see if they're identical, they just disappear. And that kind of makes sense. If you've got a wave and you're in phase with it, and it's always just like pulsar here, Earth here, and they're just moving up and down together. If you're trying to read the delay in that pulsar, you're not going to get anything. You can't get anything at all. So you need there to be some kind of difference. And that's what we're sort of measuring there. And that's where the interpretability of the gravitational wave is coming from. So it's something that is quite important to note. With this first term, you're going to have that commonly in every single pulsar timing residual that you have in your data set. So in a PTA, you have 80 odd pulsars, and they're all going to have this signal. And so this compounds in signal to noise ratio quite aggressively. It's very good. It's usually square root to the number of pulsars. And so that's going to be very obvious in your data, and we're going to be able to get that information very easily. However, this one here, the perturbation at the pulsar, that's very, very weak, and it doesn't compound, because while it's in every term, it's different at every term. The pulsar term is not common across anything, and you've got to do a lot of work to try to tease it out. The way these things are related, the two times, is that the pulsar time is equal to t, the time of Earth, minus LP, which is the distance to that specific pulsar, and then multiplied by 1 omega hat p hat. The p hat is the direction of the pulsar, and omega hat is the direction of the source. The way that I usually look at this is slightly different, and I don't think I've written it here, but it's tau, which is the time lag, and it's all that is just the time at the Earth multiplied by 1 minus cos mu. And mu is the inclination, so it's the angle in between the source on the sky, the Earth, and the pulsar on the sky. So that basically is you saying that there's some kind of time lag in between what the pulsar is experiencing and what you're experiencing at the Earth. I find it a little more intuitive, but it's less mathsy. So how we actually see it in the data is in pulsar timing residuals. So without pulsar timing residuals, our scientific field doesn't work. So we need to understand how pulsar timing residuals actually come out of everything that we've just put together just now. So if you integrate the redshifts that we've just established previously, you get them quite directly. And the reason for that basically is that if the redshift tells you like how fast the pulsar's clock is running as compared to the Earth, like right now, then the residual is telling you like how far out of step it is for any individual time step. So you want to accumulate that. If you integrate it through time, you're going to get that difference. And you're going to get that difference over like whatever pulsar time span that you're looking at. But that's basically why the residuals are defined that way, because you're trying to collect that rate through some other physical mechanism, which is time. And I'll just give everyone a second if they want to write these down. But this is just how the plus and the cross terms that we had before integrates out into the residual form. So it's still just based mainly on the chirp mass, the pulsar angular velocity, sorry, the gravitational wave angular velocity, dl here is distance to the source, and then the inclination and angle terms, so the phi terms. Okay, everyone's got it down. We're going to go to the fun bit, which is how to search for it. And this is what we're basically going to be looking at in the next tutorial as well. So when it comes to continuous wave search, you basically have two components, which is what I was just describing before. You've got the Earth term, which is common to everything, and the pulsar term, which is very individual. If you want to search for these things, then you want to search for the Earth term first. It's much more obvious. And you've got 8 parameters that you have in your usual Bayesian analysis or whatever analysis you're doing that you can search for. So you've got these two, which is the sky position. You've got I and psi, which is the inclination and the polarization angle. You've got the chirp mass and the luminosity distance. These are very degenerate with each other. So often often they're actually replaced by a different term so that they don't have ultra degeneracy in their sampling. Then we've got omega and phi naught, but omega is also often replaced with the gravitational wave frequency itself. This is the substitution that's usually done. So instead of using the chirp mass and luminosity distance, instead of using both of these, we interpret it usually through H naught, which is the characteristic strain. And we just substitute omega, which is the angular orbital frequency, directly into pi frequency of gravitational wave. It's a nice, easy substitution. So then we have all the information that we need from the global signal that's in our pulsar timing array. Unfortunately, we're not quite done. We've also got a pulsar term. This is where it gets a little more complicated. So if we have this equation that I was describing before, if if we try to evaluate that at a pulsar that's about a kiloparsec away, then we have a time difference, which is approximately 10 to 11 seconds, which is 3,250 years, more or less. In this time, in the time between the wave hitting the pulsar and then the wave hitting the Earth, there's 3,000 years of difference in the evolution. And so a lot of the evolution will completely be different. Like if the supermassive black hole binary will evolve over time, they've got different frequencies, they may not look necessarily the same. And it's also very, very, very difficult to know where a pulsar is. Like we can point at it, we can say it's there, but I have no idea how far there it is. And it has these incredibly symmetric solutions. So if I keep trying to find the correct solution by just running across that line that I know the pulsar is, what I'm going to find is symmetric, equally correct solutions until the pulsar prior just ends. Because there's nothing to say that it's breaking. The things that do semi-help is multiple continuous waves. If you add many more, you're going to get a more definite signal of where the correct pulsar position is. And then a little bit a little bit of evolution in your supermassive black hole binary, that'll kind of help too. But finding pulsar distances and using them to understand your pulsar term is very, very hard. So every pulsar brings that term. And so we end up having 8 plus NP continuous wave parameters. However, in practice, NP, this one here, which is the pulsar distance, it's very difficult to understand properly. So it's usually split into two forms. So instead of just looking for a distance, you look for a distance and you also look for a pulsar phase. Because if you separate them out, you've got a much easier likelihood surface to wander over. And it's much more efficient while you're adding a parameter. It's a little bit less cheap, but you get to the answer a lot easier. So it's actually 8 plus 2 NP parameters, which ends up being quite annoying. It creates quite a lot of parameters, and finding any sort of discrete solution across that pulsar term is incredibly difficult. If this comes up, yay! This is just like an example of a pulsar distance likelihood surface. So if I take two pulsars here, it's J1713 plus 0747 and J929 minus 3744. I don't know why I said their names, it's kind of force of habit. But these axes here are pulsar distances, and this is the relative likelihood, the log likelihood that you can evaluate when you scan over the surface. So all these peaks are completely equivalent solutions to the pulsar distance problems when you're trying to understand the pulsar term. And you can see here, while the answer is in the center, finding which of these peaks is actually correct is very, very difficult. And I'm only showing about 100th of the size of this likelihood surface. So it's very, very difficult to understand and find what the correct distance is to understand the pulsar term and use it for any benefit. But people are working on it, and fingers crossed. So all that to say, is there hope? Because if you have 8 CW parameters and then you've got, 80 pulsars, then you've got 2 NP pulsar terms, there's 168 parameters. And then for every pulsar, you've got at least another 160 parameters for intrinsic noise stuff. So it's like 300 parameters. And then you've got other noise properties that go up to about 700 parameters. And we might as well just say you've got 1,000 parameters. So when you do a continuous wave search and you're trying to actually model it correctly, you've got an enormous amount of enormous dimensionality of your parameter space that you're trying to search over. About 4 years ago, that was almost an impossibility from my perspective. It's just, it would take 3 months on 1,000 CPUs to get anywhere near that, which I tried once and I got almost nowhere near it. But now things are getting pretty good. GPUs, I don't know if you've heard of these things. Fantastic. They're so fast. They do sampling incredibly well. And if you want to know how some of the sampling magic is being done and being ultra fast at the moment, you want to talk to Kyle Gersbach and Nima Lal, because they're the people who are behind creating this thing called the Global Fit, which I don't know if I'm allowed to talk about, so I won't. But it's really good and fast, and they've got secrets. They understand computers. It's great. And also, people have created great innovative techniques. So Aidan Gunderson, who's at, I think, University of Montana, or Montana State, is it? Montana State. He's created this great package called Prometheus. And the very, very basic idea behind Prometheus is that you can take your continuous wave signal, and instead of evaluating it at every time step, you just pick the time steps that are important. And then you've got a very cheap way to evaluate your continuous wave signal rather than like a really expensive evaluation over many hundreds or thousands of arrival times in your data set. He's worked out how to do this with great success. And so his work has meant that even at very high dimensionality, sampling can be accomplished in, I think, minutes to hours rather than months. So it's very, very, the field is moving in a really good direction. And I think there is hope. We've got a lot of chances of being able to find things now because computers are great and people have found really, really great techniques. And also, my little personal opinion, I think we're undervaluing the pulsar term. I think we can investigate it a bit stronger and it might help us out a lot because I've been working on that and I just want to plug it. I think it's really cool. All in all, a little summary before we go into the tutorial. Is there hope? Yeah, probably. I think so. I think we've got a good chance. If there's a continuous wave there, I think we'll find it. The continuous wave search problem, I will say, it's really intuitive because it feels a bit nicer than stochastic noise. It's also really fun and you can really sort of like dig into it because there's so much that hasn't been done in it so far. Like the gravitational wave background was like such a focus for so long that the continuous wave space is really breaking open very slowly. And it means there's so much to do if people want to get involved and contribute stuff in there. It's a very, very easy place to make a big difference. And I'll just leave you with this really good question, I think, which is what do you think the largest contributing factor to future continuous wave searches might be? And I'm not like asking you as if there is an answer. Any answer you have is probably correct because we don't know. There's so much space to explore and develop here that if you just think about it for a little bit, you'll come up with something. It'll be a correct answer to that, and it'll be a fantastic piece of work. Yeah, I'll put these slides online, and that's sort of the general overview of CWs I have for you today. There you go. I will say after this, we'll take a little break and then we'll go into a tutorial. And Caitlin is also online, I believe, also willing to answer questions. They're also much more of an expert on this.
It would be reasonable for people to try to set up the tutorial, make sure they have important things.
Yes, I think let's take a break now, and in that break, let's just do that then. And any further questions, just ping me on Slack or just ping me on Slack or just like post in the channel and I can answer them there. I will add the continuous wave tutorial in just a moment, and then we'll be able to go through that in, let's say, what time is it? Let's say 1:35. Sound good? Okay, I just pushed the materials to the GitHub, so if you pull it now, you should have access. If anyone can just give the first version a run, let me know. Because when I did it, it all worked. But I've been burnt before. You will need a version of PTM-CMC sampler, but I think that was solved yesterday. Just looking for water regressions.
Yeah, I'm sure it's not also.
The default one from the but it's
That's good, yeah. Stop that.
it's there now, right? And then we also do.
Yeah, the break.
Maybe you could use one continuous source. Have the same thing, so the only two sources you get these. These.
Yeah, I guess we're it is the line, we have a single line.
So as long as it's one source.
Yeah.
That.
That's a really cool. Yeah, it's what I'm probably from like the last thing from my guys, stop, please stop. Like what percentage is facing this PD before you think it. But the multiple laws that you want to flat, which yeah. Yeah.
You have a signal model.
Description of oh, yeah, then yeah, just track that and maybe run simulations.
That's what you get.
What do you use best? I don't know, I don't use much that, so nice.
That little. How many politicians? Yeah.
You can look at it comfortable, so we can, we the transfer, that will see like, the concepts of the organizations who have to have these positions. So that's just a little on the agenda have. Yeah.
So,
I think it's pretty. I mean, probably that's the killer. I think it's for in the first people. Yes. And I also like the reading the word.
well, yeah, it's a, they're different, like, there's more studies, so they didn't provide, you know, the complicated, remember, like, say that, all of that, but then, like, I always think that's a big part, there's more, like, but it's not. Yeah, it's like.
There's some standardization like this. It's really just how everything can operate.
Right.
And that's where I was here.
Yeah, and then there's plus, and forward operating.
Right.
So they would do also.
Oh,
Like, nowadays, this.
so, yeah.
Yeah.
And the factor modes are both multiple trailers and for all time.
When you say it's completely don't.
Videos are so many easier. That's why we do.
That's.
You're on great. Oh,
Oh, you're. Oh. We should be, sorry. Yeah, you one more, so, deadline, yeah.
So I know.
But no, I was thinking, from the event, the balls made like, it's set up or everything is slowed down. Like, you can't pull it, like, what would, yeah, like, I guess, you like this, like, rapid acceleration, like, you just put it in balls. So, that. Yeah. There you go. Yeah, so this is, you can detect this more than just this, like. So. So, yeah, it's fun. The thing that really motivating is like very, like theoretical. It would go on when, also on class. So this is being on a little bit and but well, sorry, you can provide it and users. Because I imagine like that. Also, yeah. Still where like the component of the program.
Yeah, she was working on, there's an extension of some work. She came out of marketing husband. It was really just the last thing that we looked at in some papers. Kids are short more here. And there's a why. Then she was almost there. Oh, but you were not there. Or not if there's vaccine, you can see that, but I am right there.
Yeah, you asked questions, or you need right, this is another good question. Really not bad, there's no.
I had my seat. Lots of people are nice. I know that's just one of them. They're lying. So very scary. So they're all. They, yeah, I will see that. I
Oh, I mean, there's show wait.
well, like, starts on the main topic, yeah, sure, I'll send you. This is kind of. Yeah, try my. That's what they're like, they don't say during the song, actually, I was so bad. Yeah. We'll just.
Hello. How we going? Hey, how are you? You going good? That's good. What's new? I'm just going to quickly explain these notebooks and the tutorials. They're very self-directed, but they're split into two parts. And so there's what I've uploaded, and hopefully people have been okay to run it so far. But I've uploaded one version of each, which is sort of a choose your own adventure, have a little bit of explore, see what you want to do. There's also a solutions version of the notebook, which just fills in some of the blank cells that are in there. Most of this has been adapted from a tutorial that was put together by Polina Petrov about 2 years ago, which when I said, oh, I'll make a new tutorial, I got told, don't, it's very good. So we're sort of just borrowing that. But the first thing that I've sort of added onto it is that the first notebook is a very cheap and easy way to simulate data. A lot of people run into issues when simulating data because there's no real quick and easy way to do it. The version that I have here is very quick and easy. All you need is just an initial directory that contains pulsar, real pulsar stuff, and then it just takes that, destroys it, and builds something on top of it. So it's very quick and easy. So in the first notebook, what you should do is go through it, try to understand how the little parts of these functions that have been put together work. Try to simulate different versions of data, add continuous waves in, add red noise in, add a correlated gravitational wave background, and see how the residuals change for yourself, like really look into it. Then at the very end of the first notebook, you should be able to save that into your local school directory thing, wherever you're pulling this GitHub repository. And then in the second notebook, you'll be using the data that you created in the first one to then search for a continuous wave source. So please put a continuous wave source in the data that you simulate, or it won't work very well. So the second notebook, which I'll just get up on the screen, it mainly uses something called Quick CW, which was developed by Ben Sibekse and their supervisor at the time, Neil Cornish, which is a very efficient way to do continuous wave Bayesian analysis. My impression of why it's very efficient and good is because it has very, very intelligent jump proposals. So as it does the MCMC, it's able to skip around and jump whole groups of parameters at once so that it never manages to get stuck in a very unfortunate or unpalatable likelihood space. So it's continually moving around and always getting accepted. In this, you're going to have the option to try to search for a pulsar term. You can also turn it off, and you can see that not much changes unless you make it a very loud continuous wave, because they're very difficult to find. You're also going to see that I think the default that I have in there at the moment is going to take about 5 to 10 minutes to run, depending on the hardware on your computer. Just CPU should be all fine. And then you'll be able to inspect the chains and see if they converge compared to what you've injected. And then it'll also show you at the bottom a sky localization plot. So you can see how the posteriors that you get eventually from this Quick CW program eventually turn into a sky localization. You can see how broad that region is. And there's some little questions there that Polina put in 2 years ago, which is sort of like, probing questions of, how would you improve this? What would you do to improve this? Stuff like that. At the very end, there is an additional section to do with the use of a program called Prometheus. This is the one that I mentioned at the end of the talk. That's written by Aidan Gunderson. It's very fast, but it requires a GPU. So if you don't have access to a GPU, you won't unfortunately be able to use it. But if you do, or if you want to later, the code is there. So you can take that code and you can use it later on. It's all free for use. He's published it now, so it's all good. The difference is basically night and day. Like what takes like 20 hours for the other programs takes like 5 minutes with Aiden's method. It's very, very good, but it necessitates a GPU. He did say we'll work on a CPU, but it'll take like 10 hours, where quick CW would take 5 minutes. So, you know, you got to weigh it up. Anyway, that's the most part. Take your time, go through it. I'm going to be hanging around, and feel free to quiz me. And there's like little questions along the way, explanations. If none of them are clear, let me know, and I can come help you out. If anyone's having trouble with the programs, also let me know. I'm not good with getting programs to work on computers, but we can work on that together and we'll work it out. And yeah, enjoy. We're going to break at, it's 1:42 now. At some point, you're meant to have a hack time, and I want to make sure that you do have that hack time. In fact, Steve told me the time and I forgot it. 3:30. Okay. So we're starting a little bit early anyway. I'll give you guys a heads up when it's 3, and after that, take a break, do whatever you want to, and then we're going to reconvene for your hack time into your groups, and then the day will end shortly after that. Sound good? Fantastic. Can I get a... Can't believe that worked. Fantastic.
Yeah, so exactly. So you investigate using the various different things, so it's crazy what you're talking about. So you're going to go over the keywords of computer design. So you're creating this pulsar residuals now, also KLS, and you're setting the code residuals. So we're going to start by creating better residuals, and then I think organic. We're going to start realizing cascade processes, one more better residuals, and that's going to include the source of 6.5. So we later on, you explain, you explain, answer, you know, kind of evaluated, answer, you know, fonts, and you say, throw it into your residuals, then you go use it. So it's a very quick and dirty, like, direction. But I do everything else well. Thanks.
Yeah, I just want to see your.
Oh, the part. Is this the studio? Going man, just the phone. What? No, this is, you know, what's what you have to do.
Yeah, I just got to get her final.
You do? Oh, everything is so cycle. So if you have the directory structure properly, you do like step per card. You can, wow.
Where you take her?
Yeah, so do you have something like flexible?
Your workspace is like everything.
Yeah, so kind of, like, something specific, like, user or like in our workspace, if you put all the software that you now get out and actually, we do that. Discovery, yeah, again. So those got your own discovery, yeah. So going to. Oh, we're gonna do what? So we're gonna go to Urban Jackson's.
Just have her looking in.
So,
Is this what you're looking for?
oh, you know, so, yeah, you also open like that, if you want, but like you can directly go into the charts, like, you can go, and you can go into, like, what's scripted on possible, on possible. This, so, discovery is not it, like it. So this could change. So, I would say you just understand it generally, not specifically, to the application probably. That is, that is. This one. The. This is very positive. This stuff. Oh, okay. This is the part of the set that I use. It's something that I probably there, but I'm sure we should probably better if it's a guy very well done. Yeah, it's the first one, but I don't think so. Yeah, it's small. No, that's really for issues. Because, the value is not quite, it's going to be very, very completed, so it shouldn't be very logical. So you might like the registration thing. You use one of those so far, already with Facebook now. So it should still be fun, but it'll be hard to get good first of it. Oh, well. Okay. Almost like. Is there a distribution of the Okay, well, yeah, I can write down that this. Yeah, look at this. Yeah. Yeah, because the operation. If you make the focus available, then.
Like 10 brackets.
Yeah.
So I'm just sort of assuming.
Yeah, I think you're right. And you do it and you make the, make it a different slow. You want to start? Oh, I didn't. Good back. So. So yeah, it's just all, yeah, cool. Also, the panel that you follow mass out to the single bar, or just like, at least leave the PTA. Then you read your option. You read your option.
Those, so try to get.
Oh.
Basically, it's a very normal, it's in all very exact cast, and then calculate the. I mean, no. So it's all back to the right line. Yeah. When I don't, when I was on this small player. There's some weird discussion, worlds where I was here later.
Oh.
But keep it going. This is no. This gives you how these are. And you can learn it. That was great. And it's still.
Are you sharing things like are you shooting?
I'm increasing all the source parameters and correction. Set that.
And you're showing you know the also the ground, so you
I'm assuming there is a. Yeah. That's yeah. That's when comes to create CW signals and several. Yeah.
it's there the wrong thing, but it is there's nothing, it wasn't going to share and the black stuff was there. Right. Yeah, you know,
They also. I don't know, the 80-90, revolution, it's average. So bad.
oh,
You don't get that in here, part of the time, but.
you're
Stay high. That's. I'm sure.
I heard about this.
So. You do this continues to.
This is a non-volatile, this is a non-volatile, this one. So I was engaging the non-volatile, it's very, safe, very bad also. So, yeah, so you get these marks, because like you have like the downstream one dimension, I already do correct answer, because the way it's just cycle. As then when we look at the three dimensions, you get like downstream multiple correct answers, we always need, with the way it's cycle.
In overall, if you have way bigger process, then this would end up being probably higher than the likelihood if you're offset 20. Right?
No, that's what happened. So for example, when you're wide, you're all within the time. Yeah, the right structure is evolution, but irrigation, don't get significant evolution. So you're gonna give a quality difference. Like, well, is the, you go off, you go all across. So, first, you go to the area well, which, all, is the record. So, we got all, here's what it is. Is, writing, the, so points.
You're kind of offset or negative.
Oh, no, it's just all there's kind of function.
Something, right?
Yeah, but this region where it's basically indiscernible, right? That is years in this region, where they're all the same. And the ends, I got always saying that still stands like high. Yeah, so it's very, very difficult. Maybe one also, we might have one or two pieces, it's a thousand. We really don't make it good at all. But in the industry, it's pretty much straightforward.
So, if you know the distance really well, this kind of involving the travel clear.
It doesn't roll off, but it's the physical boundaries for where the waves exist. So it stays the same, but you're out of the, so you might feel it will fit, but it will be there. Because you're not that far. So the drawing off thing comes from the actual a lot. Good, and they want very much. It drops off. There is some form of collision, there's some form of like I pulsar stuff that it just where this all possible there. So it's kind of but usually the section, that section is huge.
So, you want to be regulating it so.
Yeah.
Is it basically saying like, okay, no distance came, not a thousand?
If you know the distance within one of these peaks,
Then, and then back into that.
you're probably a source of friends, you don't get better significant ratio one source. You don't get not the one relation, you're gonna get the show through that action down evolution. You see yourself, like you see that with what about population rates. If you get one of these markers, then it's a massive extra efficient action. Yeah, but this is like you're going along process. Yes. Yeah. So, just try almost in fun with it. Just try standing budget. Is what I deserve. I don't know if it was. I'm just gonna I will do
So what happened? It doesn't work. What? Jack, I'll try to. Are you sure? It makes it through Jack's. So if you go into the sample over. The multiple idea is not Jack's. What the other great things say? Libre of those, is there a chance over for that? So, because it's good. Oh, this is the high one. Like, it's just the correct function. Yes, it's empty. Strategy. So I would hit praise for all jobs. That might. By installation, I'll just. And so.
Jazz out and I can just so I can put it on the jazz. Just because I did the jazz for. The jazz are amazing.
Well, I should be.
It's really second.
Oh. This is just theory. Yeah. They're going to So scanning is just. Yeah. So no, it's just that it doesn't seem to be it's just so. This is what. Oh, did you see that? Um. This is very close inside, very close. Then. I think that's what there's somebody. I think it's all it's being so I recommend. Well, I mean. Yeah. I cannot. Okay, so you're exactly off that. No, I'm getting to the role. And the only thing I should have was just. Sorry. So it's nice to see you. Wait, so what was your? It's a maximum recurring. This is the. Well, it's like it's anything like that. It's like it's like. It's right on. It's like that.
Yeah, it's not incredible. Sci-fi, no, choice. We're starting.
Oh, I see. So my friend wants to. Well, it says no, it's right there.
Yeah, it was just fine.
Like, I think every other single thing we use is that. Yes, that's around.
Yeah. So, what if you? What if you did? Try, this is unique situation. It's not where it's not what position.
I think I just worked it out. About 5 to 10 minutes if it's in the default stuff. How much is running for you? An hour? Alright, give me a sec. Yeah.
I've been trying to do it.
Well, I'll be with you a sec. That smacks of not working. I'll be with you a sec.
That you think, restarting back, or just need to run, or, okay.
I not when I'm meeting environment, or I'm
Sorry.
environment, so I hate.
Yes. Oh.
So we gotta do it through the time.
I will answer the first one.
Yeah.
So, because of how we're, you don't want to.
Very good.
So it says, student ranking of student reaction, so it's saying, student students for the injection. Doesn't say if the cost, and then bring it on again. It's just in a way to. Yeah, that's right. So you can see, you know, your objection, like from two years, the price something that's around the dollar, instead of meters.
Oh, it's maybe.
Yeah, I think that's what.
For your starting. So is anybody in the UV way of installing when you come out here for the from? Yeah.
No, no. Hold on. I have error report them code.
What is the frequency that that's coming out?
Some sort of open issue that we can,
Wasn't the. Basically, go through this.
Doesn't project.
Typically, there's something wire we use for install.
Well, we have. No, I have.
Okay, given nobody seems to be, since QuickCW doesn't seem to work in the way that I wanted it to, here are some installation instructions. A lot of these are cont'd, but I think maybe if you install an editable pip version, that'll probably sync into the UV environment, but it might also break that. But give this a go if QuickCW doesn't run on the UV sync. Yeah, how do you zoom? There you go.
Are you?
The issue is that center to it's, I don't understand a lot of stuff like that. It seems to be on like good, like Chinese or not paid. Yeah, so this here is city friends, maybe stop with my phone, so I can see also like. That's all I can. Yeah, I'm gonna do all the stuff. Oh.
I reduced it for change.
It does have a lot, and I've said this, I'm going to say, the fix I have is just the dictionary. So, the other option is that means that you, it is that when you update this dictionary, you update this definition. So, always once a year, you bring up this, bring the new dictionary instead of the different dictionary. See how it works. I think if you do like this, because with friends.
I mean, I'm not
Yeah, you different stuff, so I'm just the first one.
Oh, yeah.
Yeah, it's like. I know, they said it's trying to be kind of. So I. Yeah. Uses
If I change the source position, it changes. So it's not like,
The source position changes.
if I change the source position, this effect changes. So it's also, so it's like it's something that shouldn't be related to the pulsar. It shouldn't be related to the source, so it might just be something.
I think it's got to be something that's coming out of this, like, because that's where it's being updated, I think.
Because here I just changed. Like I rotated it by around degrees.
And that works. That changed it.
So say this is what happens now. So if I change this to 90.
Yeah.
This
But
if I go back to this and then I had it's gonna be, oops, I multiplied it, so the declination doesn't change as much. Calculation does something. But,
I think like it's getting, it looks like it's getting updated. But there's
Yeah.
some minimum version of it, which isn't being updated or something.
yeah, it's weird. I don't know, we figure it out.
Yeah. I don't know, keep chugging along and then I'll see if I can fix it.
No, you don't have to, like,
No, it's like,
I'll look at it on my screen.
no, I don't think it's just you. I think it's like probably a lot of people, so I'll fix it.
This is.
Hey, yeah,
Sorry,
that's all right.
is this familiar at all? This is when
No threading, what?
it's,
Oh, yes, you don't have open MPI.
should I just follow that command and install it?
Yeah, give it a go. Yeah, yeah.
But because it's UV, what one would do like UV pip install? So this isn't the UV environment.
This isn't the UV environment?
This isn't the UV.
So this is a condo environment?
No, it's not, this is the environment we set up.
Okay,
for the
right,
class.
right.
Yes,
I think we just do pip install.
yeah,
Pip install should still install into UV, I think. Give it a go, see what happens, yeah. If it
Okay.
doesn't, I'll find a way to make it work.
okay, all right.
Good try.
I thought it was a simple.
Yeah.
Something like this.
Looking at that, I saw your videos going. It's also just a bad. It's a bad sign for the. This is not gonna go up. It's not red. It's not red, I saw.
Like, just.
Oh, yeah. Same. That's how I initially was. Yeah, but I don't. So I think I'm running to get a different version of it. Check your version on the service. I think I can just as well. Oh, I think. So it's a reference here the it's like, you know. We're going to. You need to have a lesson to see. Should I just add and also pretty sure? Yeah. Yeah. Great. Oh, yeah. Oh, all right. I tried listening. Oh, yeah. Might as well just the ball. Oh, yeah.
But it's not there.
Like I originally used everything, and so, and it didn't work. And so it's very, I just created a new font. I got the same.
They run just running for.
Yeah, it's just saying I need this.
Okay, you shouldn't run those much more than on mine, I ran my head.
I gotta install this, I don't think that this.
Oh, all those, it's very already recorded, so
Yeah. It's there, it's didn't tell like that.
Yes, sir. Very.
We are getting the same. I created a new environment only for the.
Oh.
Then.
Okay. It sounds good. We're not getting construction stuff.
If you can, it's okay.
No, it's a nice, isn't it?
Yeah. No, I think I thought that.
Yeah. Yeah, so this. Where is it, sorry? Yeah. The P dist so is sorry. Where you give the priors. No, this is yeah, okay. Okay, so this P dist is the uncertainty on the pulsar distance.
Yeah.
Just that.
Yeah, so it's the pulsar distance parameter here is the uncertainty on it. There's another like p-dist parameter that's in it, which is the actual pulsar distance applied to it. But this is the relative uncertainty. The thing that gets taken into account in the delay function is the relative uncertainty.
Okay.
I think so, those p-dist. Yeah, so I think there's normal 0, 1, so it's like mean of 0
Yeah.
and 1, so it's centered on the p-dist that's in the pulsar itself. So that should be fine, I think. So like there's other ways to inject it, but I think if you want to play,
Yeah, no.
if you go into that's going to do it. Oh, where do you load? Where's P? Where's this? Yeah, it's right here. Like if I go to P loading.
I think you have run over like the kernels were.
Oh, okay. Yeah. Yeah, let's go. Let's do this because they live here. I go P.
It was, you know, nice.
Pulsar, okay.
That's good to know.
Working by its side.
It's working.
Oh, the other
Yes.
pulsar is also cool. Oh, it's pulsar like. Okay, yeah, whatever.
Okay.
So in here,
Yeah, that was.
how does further pulsar? Dot, will tell me.
Yes.
There you go. So it's saying that like
That's
this,
the distance and
that's the uncertainty. But so
Yeah.
what it's doing is it's taking this distance and it's applying that as the mean, and then it's going to give you a 1 sigma uncertainty at either side of that.
Oh.
So that, so when you're setting up the normal, because it's not a uniform prior, it's a normal prior.
Mm.
And so what is happening behind the scenes is the prior is randomly, it's randomly creating a pulsar distance out of this as the mean of the signal.
Okay.
Yeah.
Like if it's L0, I say, so it's creating a distance L and then like L minus L0 whole square over sigma square.
Yeah, I think so. Yeah. It's just trying to apply that. Yeah, and then it's going to randomly grab from that.
I see.
And then that's going to be your like true pulsar distance.
Okay.
Even though it's actually not what this is, but it's just the simulation part. Yeah. Yeah, that's good.
And I said, you know what, I said. Not that it changed anything. And then there's about some. Yeah. The flesh. And if I'm trying, I'm just like, if I try to use. I can't be. I'm not choosing. Sir. Yeah. I guess. All your. That's it, you can see that really, you can see. I've figured out. It hasn't been fine. Because it's all visibly not that. Already. I'm just wondering if we came under pulsar. It's not a deal. Also, yeah. In my head, I just think of what's talking about. Yeah. You need to take me back to take on my. Is yours working? Well, that's Yeah, I mean, I think. But if they start making, you know, I'm saying that you have to, you know, I think after sex.
You were.
Not that.
Yeah. Yeah. Never got past 0%. Like this. So if we go by. Yeah, it was probably.
So I mean, it's, you know, yes.
Oh, I want to, I want to say, I want to do this great. It's so. As you. Say, what's next? Oh, it's very nice then. Yeah. So.
Okay, yeah, no worries. So. Yeah, you don't know what you're about this. I should just start. Yeah.
I'm just trying to. What I'm also, I'm trying to figure out is, they're gonna have to learn in the back of the. The fryers or injection.
Like I said.
That will run then. Happening, with that also. Recommends that. Like, the year after the system slash. And like I say, it's. Yeah, we do that time.
But what I've done is because I did this.
Okay, yeah.
Yeah, but you can just say, you know, this, but when I did that, I got an error. Because that's what I did before, because that is the same thing as doing it here. This is the same. Like if I change this to constant, here's the other one.
Surely that. How would you randomly decide if you're gonna make you're rolling on it still? So. I don't know that because like the answer one or two you see. You have to go outside and back on the actual ball. That is when you check that you're not the best. Yes, every time you agree, I'll do that one. Yeah, and then when you have, you go under down, that's how you take it. This is virtual reality. I think.
It's just an issue because I need to do it like, yeah. Yeah, I know, so the issue is just, I need to know something that I need to find in the back. I know, that's not gonna speed it up, you should try to speed it up, so that way this is moving, but, because then I'll sort of say around. Yeah, so I just need to figure out how to get it to not have that start. Okay, but so.
Hello, everybody. Hello. We're about to enter the final stage of the day, which is your hack time. So take, a couple minutes, go relax for a bit. You got 15 minutes to relax or however much time you'd like to. And then you can start stressing out again when you get into your hack time and start doing the stuff. But it's completely up to you what we're doing here. If you're having specific problems with the tutorial I put together, because I think I've seen a lot of change now, but some of them look good and some of them don't exist. If you do have specific problems, if you send me your problems, I promise you I will fix them. And I will give you a version of that notebook that works on your computer. If you have an Intel MP problem, if you've got a Silicon Mac, I don't know how to fix that, but I can work it out somehow. Anyway, have fun, relax. I was about to say I have nothing else to say. There we go. That's my second goal.
That's good. You don't really need this. Or how you go around. And like, I have no idea, and I'm very proud to commit to the plan. Also, but then, yeah, I just think this thing, Joe, yeah. Yeah, but I think, yeah, I mean. Think about that. You probably get a record. I think it's going to say realization allowance, going to buy realization allowance, option involved. Oh, you sure? You know, Yes. Next side of the pulsar, it's really kind of almost chat. You go there, like, no, you don't, like, not. Yeah, no, not saying part of it. It is so. Yeah. It's really easy to fall with, obviously, that doesn't probably. Not very. It's actually going for. That's all plastic, right? It's really well put together. I'm very, very well. This is not. Stuff. Oh, you know what it is? Indian type research. Well, yeah, I'll take Yeah. I mean, I've never used this stuff in a long period, so I have no better. Yeah, this is just. Really? Okay, well, it works, that works then. Well, so it's not on our thing to works. There you go. Start. Yeah, it smells good. Yes, a lot. I can only see your head. Oh, it's just. Yeah. Any presentations, I guess some of this I came. My location. But it has to be made, they would have to. Oh. I'm very rushed it. I'm these are the questions. Not change up. Yeah, I'm trying.
I was just gonna put on some inspirational hack music.
Yeah.
It's a good channel. I listen to this a lot.
Oh. The VIPER. Easy. I listen to that. Okay,